Beneath our feet lies a world we rarely consider, a world that does not shimmer with color, or echo with waves, or glimmer beneath the sun. It is the unseen interior of our planet, the silent depth upon which every step of life depends. The ground beneath us feels solid, dependable, immovable. Yet this surface we know, the soil, the stone, the continental plates, is only a whisper-thin shell resting upon an interior of unimaginable scale. The earth, for all its firmness, is layered like a slow-turning sphere of time, and between those layers lies one of the greatest frontiers of geological mystery, the Moho Discontinuity. It is not a place one can visit, not a chamber or cavern to be entered. It is a boundary, invisible yet absolute, where the crust of our world ends, and the mantle begins. The existence of such a boundary was not always known. For most of human history, the ground beneath us was simply the ground. Mountains rose, earthquakes shook, volcanoes erupted, and these phenomena were accepted as part of nature's breath. But as the science of seismology began to mature in the early 20th century, a Croatian scientist named Andrija Mohorovičić noticed something peculiar. When an earthquake struck, the waves that traveled through the earth behaved in ways that could not be explained by uniform rock. Some waves suddenly accelerated at certain depths, changing direction as though refracted by a hidden surface. Mohorovičić realized that these waves were not simply passing through one continuous body of stone, they were crossing a boundary, one that marked a dramatic change in composition and density. In that insight, the Moho Discontinuity was born. Though the Moho is named after him, Mohorovičić never saw it. No one ever has. It lies tens of kilometers beneath the surface, sometimes as shallow as 5 kilometers beneath the ocean floor, and in other places more than 70 beneath towering mountain ranges. We know of its existence only through echoes. When the earth trembles, seismic waves pass through its layers, and those waves carry back the story of what they have encountered. The Moho speaks in these echoes, not as a sound but as a shift, a sudden jump in the speed of seismic waves that reveals the passage from crust to mantle. It is a conversation in vibration, one that takes the patience of geologic time to interpret. The crust above the Moho is our familiar world. It is the foundation of continents, the source of mountains and valleys, rivers and plains. It is composed mostly of lighter rocks, granite on the continents, basalt beneath the oceans. Below it lies the mantle, which is neither molten nor entirely solid, but an immense mass of slow-moving rock under such heat and pressure that it flows like a dense, viscous current. Between these two layers, the Moho marks a sudden change in mineral structure. The crust's lighter silicates give way to denser peridotites, and seismic waves, sensitive to these changes, accelerate as they enter this deeper realm. It is as though the earth's very breath quickens beneath its skin. To contemplate the Moho is to confront the vastness of the unseen. We measure mountains in meters, oceans in kilometers, but the Earth's internal boundaries exist on scales we perceive only through mathematics and imagination. The Moho is deeper than the deepest ocean trench, farther away than any human excavation could reach. If one were to drill straight down through the Earth's crust, descending past granite and gabbro, through veins of mineral and pockets of molten intrusion, one would travel for hours through an ever-thickening silence. The rocks would grow warmer, the air vanish, the instruments tremble. After tens of kilometers, the transition would come, not as a visual line, but as a transformation in the very fabric of the rock. The minerals would rearrange into denser forms, the structure of the earth subtly shift. One would not see the Moho, but one would feel its crossing in the language of physics, in the rising hum of seismic velocity. The Moho is more than a line in the earth, it is a threshold in understanding. It represents the point at which the rocks of the crust, formed through volcanic eruptions, sedimentary deposits, and tectonic compression, cease to exist as we know them. Beyond it lies the mantle, where minerals are forged in the crucible of heat and pressure, cycling through convection currents that power the drift of continents above. It is a place of profound transition, yet it is not abrupt. The change unfolds across several kilometers, a gradual blending from one realm to another. The word discontinuity suggests a break, but in truth, it is a gradient, a quiet metamorphosis that defies the simplicity of human language. Even now, we do not know its full nature. Scientists debate the precise composition of the rocks at this boundary. Is it a sudden mineralogical shift, or a chemical change, or a relic of ancient melting processes from the planet's formation? The Moho is known everywhere, yet fully understood nowhere. Its depth varies, its properties shift from continent to ocean, its clarity fades and sharpens depending on where one listens. It is the heartbeat of geology, steady yet ever-changing, an echo of the Earth's earliest differentiation. Attempts to reach it have tested the limits of human engineering. In the 1960s, an ambitious American project known as Project Moho sought to drill through the oceanic crust to reach the Moho. Engineers believed that the thinner oceanic crust offered the best chance of success. But the ocean proved a difficult ally. The machinery struggled against pressure, temperature, and the unpredictable movements of the sea itself. The project was eventually abandoned, its deepest boreholes falling far short of their goal. The Soviets tried again in the 1970s, drilling on land at the Kola Peninsula. For years they pushed deeper, their drills biting into the Earth's crust until, at over 12 kilometers, they reached the physical limits of technology. The heat and pressure at those depths, enough to warp metal and boil drilling fluids, brought the effort to a halt. The Moho remained untouched, another horizon beyond reach. And so the Moho endures as both a physical and philosophical mystery. It is the line that separates what humanity can touch from what it can only imagine. It reminds us that even in an age of satellites and supercomputers, there are still frontiers beneath our feet. Every tremor, every distant earthquake that ripples through the planet, sends us faint reminders of that hidden interface, where the crust yields to the mantle, where the familiar world of rock gives way to something deeper, denser, and older. The Moho hums there in silence, patient and eternal, a whisper at the edge of what can be known. When the earth trembles, it speaks in a language of waves. These waves are born in sudden fractures deep within the crust, moments when rock, stressed beyond its limit, breaks and releases its pent-up energy. That energy moves outward, not in a single pulse, but as a complex web of vibrations that travel through every layer of the planet. To most of us, these tremors are fleeting sensations, an unsettling shiver beneath our feet, a vibration of glass on a table, but to geophysicists, they are messages, coded in the language of speed and reflection. Each earthquake, large or small, is a natural probe of the Earth's interior, and among its many secrets, it carries whispers of the Moho discontinuity. There are two main kinds of seismic waves that carry these messages, the swift, compressional P waves and the slower, shearing S waves. As these waves pass through different materials, their speeds and paths change. In air, they travel sluggishly, in rock, they accelerate. The transition from one material to another, from granite to peridotite, for instance, creates a discontinuity in speed. That discontinuity is the signature of the Moho. When an earthquake occurs, some of its waves pass straight through this boundary, while others bounce or bend, refracting like light entering water. Seismologists measure the arrival times of these waves at stations scattered across the world. The tiny differences in timing, often mere fractions of a second, reveal not just the depth of the Moho but its texture, its thickness, and the nature of the rocks above and below it. It is a strange art, to see through sound. Unlike light, which travels in straight lines. Seismic waves curve as they move through layers of changing density and pressure. The Earth acts as a lens, bending and focusing its own internal echoes. With enough data, collected from hundreds of quakes, recorded by thousands of sensors, a picture begins to emerge. It is not a direct image, not a photograph or a slice of rock, but a map of speeds, a model of how the Earth resists vibration at different depths. In those models, the Moho appears as a sharp boundary, where velocities suddenly increase, often from about 6 to 8 kilometers per second. That jump tells the story of transition, from the lighter silicate crust to the denser, magnesium-rich rocks of the mantle. Early seismologists were astonished when their instruments revealed this hidden architecture. They realized that the Earth's crust, once thought to be a single, unbroken layer, was in fact astonishingly thin, a fragile shell resting upon an immense, dynamic mantle. The revelation was humbling. Beneath every mountain and ocean lies the same thin partition, no thicker in proportion than the skin of an apple. And below that, the mantle extends for nearly 3,000 kilometers, a slow-moving sea of solid rock that convects, deforms, and drives the tectonic plates above. The Moho is the seam where those worlds meet. Each new earthquake refines our understanding. By comparing how waves travel through different regions, beneath oceans, beneath continents, beneath mountain ranges, scientists can trace the undulations of the Moho. In some places, it lies shallow and distinct, in others, it fades, blurred by heat or mineral mixing. Under ocean basins, where the crust is dense and young, the Moho is often sharp and easy to detect. Under old continents, built from layers of ancient collisions, it becomes more complex, its signals scattered by faults, intrusions, and metamorphic transitions. To study it is to engage in an act of patience. Each tremor adds one more faint brushstroke to a picture that has taken decades to assemble. The result is a global mosaic, a seismic topography of the unseen. Across this map, the Moho rises and falls, deepening beneath mountains, arching upward beneath rifts, rippling beneath ocean ridges like the fabric of a slow-breathing creature. These subtle variations tell the story of Earth's evolution, how continents collided, how oceans opened, how crust was born and destroyed. Yet, even with our most refined instruments, the Moho remains elusive. It does not always behave as expected. In some regions, seismic waves that should reflect from it arrive weak or scattered, as though absorbed by something complex or partially molten. In others, the expected sharp jump in velocity is replaced by a gradual gradient, suggesting a zone of transition rather than a clean break. The Moho is, in this sense, not a line but a region, an interface where minerals shift slowly, their structures rearranging under immense pressures, blending crust into mantle like dawn blending night into day. Modern technology has deepened our hearing. Arrays of sensitive instruments called seismometers now carpet the planet, recording vibrations so faint that no human could feel them. Even the quiet hum of ocean waves crashing against distant shores creates seismic noise, and from that noise, patterns emerge. Using techniques called seismic tomography, scientists can now create three-dimensional models of the Earth's interior, revealing the shape of the Moho with astonishing detail. In these models, the boundary undulates gently beneath the continents and plunges sharply beneath mountain belts, forming folds and valleys invisible to the eye but revealed by the mathematics of motion. In the quiet corridors of seismology labs, these models glow on screens, fluid, color-coded renderings of depth and density. The Moho appears not as a static surface but as a breathing membrane, changing shape in response to the slow, relentless motions of the crust above. In some regions, earthquakes themselves are born along this boundary, where stresses accumulate until the brittle crust fractures against the more ductile mantle below. In others, the Moho marks the end of motion, a zone of stability, where ancient rocks rest unchanged for eons. To those who study it, the Moho is a paradox, both a line of separation and a link of continuity. It divides two worlds but also connects them. The crust draws its magmas from the mantle, and the mantle receives sediments in slabs of crust that are pulled downward by subduction. Energy flows both ways, upward through volcanic plumes, downward through the slow sinking of tectonic plates. The Moho is the meeting place of these forces, the invisible negotiation between what rises and what falls. And so the Earth's heartbeat, though inaudible, can be traced here, in the vibrations that cross this buried horizon. Each quake that rattles a distant shore sends its signature through the Moho, and each passing wave carries a fragment of its story back to the surface. Over millions of years, those vibrations have written a quiet chronicle of balance, of tension and release, of birth and renewal, of boundaries that endure even as they shift. In the early years of the 20th century, when the Moho was still a newly discovered enigma, humanity began to dream of touching it. The idea seemed simple enough in thought: if the Moho was the boundary between the crust and the mantle, then perhaps, with enough patience, one could simply drill down and reach it. Yet that thought would soon collide with reality, the overwhelming difficulty of moving from imagination into the depths of a living planet. For the Earth, though solid to the touch, reveals itself as an unforgiving labyrinth of pressure, heat, and resistance. The deeper one goes, the less it behaves like a familiar world and the more it becomes something alien. Still, the dream persisted. It became one of the great scientific ambitions of the mid-20th century, to reach the Earth's mantle, to bring up a piece of it with one's own hands, to turn the Moho from theory into touch. The first true attempt to make that dream real was Project Moho. Its very name was born from the Moho itself, a playful shortening of Mohorovičić hole. Conceived in the 1950s by a small group of American scientists, the project was meant to be both daring and symbolic. This was the age of spaceflight, of exploration turned upward toward the stars, and yet here were a few geologists asking to go in the opposite direction. They wanted to explore inward, toward the deep unknown beneath our feet. They imagined drilling through the seafloor, because there, the crust was thinner than beneath the continents, sometimes only a few kilometers thick. By choosing the ocean, they hoped to reduce the distance to their goal. It began not in a lab but in a meeting between visionaries. Walter Munk, Harry Hess, and others gathered under the banner of the American Miscellaneous Society, a group that thrived on impossible ideas. To them, Project Moho was not just a scientific experiment, it was a symbol of human curiosity itself, an attempt to pierce the last untouched boundary on Earth. Funding was secured, a test site chosen near the coast of Mexico, and in 1961, a vessel named Crust sailed into the Pacific. It was a converted barge, crude and makeshift, yet fitted with an innovation that would change ocean drilling forever: dynamic positioning. Instead of anchors, the ship used a system of propellers and sensors to hold itself steady over a single point in the ocean, compensating automatically for wind and current. This allowed it to drill a precise hole into the seafloor, even in open water, a feat never before accomplished. The results of that first test were, by every practical measure, extraordinary. The team managed to drill more than 180 meters into the seafloor, retrieving samples of basalt that offered rare glimpses of the oceanic crust. Yet the Moho remained far below, unreachable still. What they had achieved was not the destination but the first step. Still, in the minds of scientists and the public alike, it felt like the beginning of something monumental, a prelude to a future in which humanity might one day hold a piece of the mantle. Newspapers hailed it as the Earth's equivalent of the space race, and for a brief moment, the world turned its eyes downward instead of up. But ambition often outpaces reality. As the project expanded, it became entangled in politics, cost overruns, and competing interests. Scientists dreamed of drilling deeper, bureaucrats demanded justifications, engineers struggled to design equipment that could survive the growing pressures. Every meter downward required new materials, new tools, and new patience. The deeper the hole, the higher the resistance. The crust, unyielding and variable, shattered drill bits and swallowed instruments. By 1966, after years of debate and financial strain, Project Moho was cancelled. Its dream had sunk beneath a tide of uncertainty, leaving behind only fragments of data and a haunting realization: reaching the Moho was not merely difficult, it was almost impossible. Yet the failure of Project Moho did not extinguish the dream. In the Soviet Union, a parallel effort began, fueled by both scientific curiosity and the quiet rivalries of the Cold War. If America could not reach the Moho, perhaps the Soviets could. Their engineers selected a site on the Kola Peninsula, a remote region north of the Arctic Circle, where the continental crust was thick but stable. In 1970, the drilling began. What followed would become one of the most extraordinary and haunting undertakings in the history of geology: the Kola Superdeep Borehole. Unlike Moho, which aimed through the ocean floor, the Kola project struck directly into ancient continental rock. The goal was modest at first, to reach 15 kilometers. But as the years passed, the ambition grew. Layer by layer, the drill descended, passing through formations older than life itself. Each core brought up from the depths was a window into deep time, a physical record of the planet's memory. By the mid-1980s, the borehole had reached a depth of over 12 kilometers, and by 1989, it achieved its final depth, 12,262 meters, the deepest artificial point ever made on Earth. Yet even at that staggering depth, the Moho still lay far below. What they found instead was heat. At the bottom of the borehole, temperatures soared to nearly 180 degrees Celsius, far higher than anyone had predicted. The rock there behaved more like plastic than stone, making it impossible to drill further. Instruments failed. The borehole itself began to deform. It was as though the Earth were quietly pushing back against intrusion, sealing itself in slow motion. The project continued for a few more years, gathering data that would reshape geology, but by the early 1990s, it too came to an end. From its depths came revelations that rippled through science. Seismic data had suggested that at around 7 kilometers beneath the Kola site, there would be a transition corresponding to the Moho. Instead, the drill found no such boundary, only fractured, metamorphosed rock. What had been assumed to be a sharp discontinuity was, in reality, something far more complex. The seismic signal that once seemed to mark the Moho was now understood as a zone of transformation rather than a clean divide. The Earth, it turned out, did not obey our neat conceptual lines. Its layers blended and shifted, each more complicated than the last. The Kola Superdeep Borehole became more than an engineering project, it became a metaphor for the limits of human reach. The deeper we went, the less we understood. The more instruments we lowered, the more the planet revealed its refusal to be conquered. Yet that refusal carried a quiet grace. For scientists, it was not defeat but humility, a reminder that the Earth is not an object to be opened but a companion to be listened to. The Moho, though still untouched, had taught us more by remaining out of reach than it might have by surrendering a fragment of stone. Today, the Kola site is silent. The borehole has been sealed, its entrance capped with a rusting metal plate, often mistaken by visitors for the lid of a forgotten well. Around it, the tundra stretches vast and unbroken, the wind moving over the landscape like an echo from the deep. Beneath that ground lies the longest human incision ever made into the earth, and beneath that, still untouched, the Moho continues to wait. In the decades that followed the silence of the Kola borehole, humanity did not abandon its fascination with the Moho, it simply changed its approach. Instead of drilling downward through the land, scientists turned once more toward the ocean, where the crust thins beneath the weight of water and time. The oceanic crust, unlike its continental counterpart, is born and reborn along the mid-ocean ridges, places where the Earth's mantle wells upward in a slow, perpetual exhalation. Here, at depths of thousands of meters, new crust forms as magma cools in the darkness, and here too, the Moho lies closer to human reach. The ocean floor became the new frontier, not as a place to conquer, but as a quiet laboratory where the planet's most ancient processes could be observed. Modern exploration found its instrument in the deep-sea drilling project, a direct descendant of Project Moho's vision. When the drilling ship Glomar Challenger first set sail in 1968, it carried not just technology, but a lineage of patience. Its mission was to study the structure and evolution of the ocean basins, to sample sediments and rocks that recorded the slow drift of continents and the birth of new crust. Over the next decade, the ship drilled hundreds of holes across the world's oceans, recovering cores that told the story of the planet's shifting skin. The Moho remained below reach, but the data it revealed reshaped geology, confirming the reality of plate tectonics, the grand unifying theory that described the Earth as a restless mosaic of moving plates. The successor to Glomar Challenger, the JOID's Resolution, pushed the work further. With more advanced technology, it could drill deeper, hold steadier, and operate in more extreme conditions. From the Pacific to the Indian Ocean, it traced the boundaries where plates met, collided, or diverged. In its cores, scientists found basaltic layers that once formed the crust mantle boundary at spreading centers, tiny, solid fragments of what might once have been near the Moho itself. For a brief moment, the dream that began with Project Moho flickered back to life, this time not through a single heroic attempt, but through the patient accumulation of evidence across decades. Yet the ocean's depths posed their own barriers. The pressures at several thousand meters below sea level are immense, the temperatures unpredictable, and the logistics overwhelming. To drill from the surface, through kilometers of water, and then through kilometers of rock beneath that, is to operate at the edge of what machinery can withstand. Each meter downward increases the risk of failure, of losing the drill, of shattering a bit of steel that took months to design. And yet, despite those challenges, the work continues, driven by the same quiet persistence that has always accompanied the pursuit of the Moho. In the early 21st century, a new vessel took up the torch, Japan's Chikyu. The name means Earth, and it was built specifically for one purpose, to drill deeper into the seafloor than any ship before it. Its design incorporates a massive, hollow riser pipe that stabilizes the borehole and allows for circulation of drilling mud, preventing collapse and cooling the bit. It can hold its position over a single point in the ocean using advanced dynamic positioning systems that adjust continuously to currents, winds, and waves. With this vessel, humanity's reach once again extended toward the elusive boundary. The goal of Chikyu is both simple and staggering, to reach the Moho beneath the oceanic crust. Several potential sites have been studied, places where the crust is relatively thin, such as the Costa Rica Rift or the waters off Hawaii. To reach the Moho there would require drilling more than 6 kilometers beneath the seabed, itself several kilometers below the surface of the ocean. The scale of such a task defies easy comprehension. From the deck of Chikyu, the sea appears calm, endless, reflective, but beneath that calm lies a column of pressure and distance that rivals the height of the tallest mountains. The ship's crew works in shifts around the clock, maintaining an unbroken chain of attention, for even a few seconds of inattention can mean the loss of equipment that costs millions. But what drives this persistence is not glory or conquest, it is knowledge. The samples retrieved from the seafloor carry within them the fingerprints of processes that have shaped the planet since its birth. The Moho is not just a boundary of rock, it is a boundary of understanding. To touch it would be to hold in one's hand the moment where the crust ceases to be crust and becomes the mantle, where basalt gives way to peridotite, and where human perception begins to blur against the vastness of geological time. What makes the Moho so mysterious is that it is not directly visible. It exists as a sound, a reflection on a seismic chart, a shift in wave velocity. To scientists, it is both a place and an idea, an interface that reveals itself only through the behavior of energy passing through it. Seismic waves generated by earthquakes or controlled explosions travel through the Earth, and at a certain depth, their speed abruptly changes. That discontinuity in velocity is what defines the Moho. Yet even this definition is imperfect, for the boundary is not uniform. It rises and falls, like the contours of a buried mountain range, varying in depth from as little as 5 kilometers beneath the oceanic crust to as much as 70 beneath the great continental shields. The Moho beneath continents is older, colder, and more complex, a record of ancient collisions, subductions, and reconfigurations. In some places, such as beneath Tibet or the Canadian Shield, it has been folded and thickened by eons of tectonic compression. In others, it has been thinned and stretched by rifting and plume activity. The Moho beneath the oceans, by contrast, is young and smooth, formed continuously by the slow spreading of the seafloor. Its composition reflects the chemistry of the mantle below it and the cooling history of the magma that once emerged at ridges. Each of these variations holds clues not just to local geology, but to the evolution of the entire planet. Modern geophysics has made it possible to map these hidden landscapes with extraordinary precision. Networks of seismometers record the subtle tremors that ripple through the crust, converting them into three-dimensional images of the Earth's interior. Supercomputers simulate the propagation of waves, revealing where density and temperature change. Through this quiet listening, scientists can trace the Moho as though reading the pulse of the planet. In a sense, every earthquake becomes a conversation, between the surface and the deep interior, between the past and the present. And yet, even as our models improve, the Moho retains a kind of silence. It remains elusive not because it hides, but because it is dynamic, constantly reshaped by heat, pressure, and time. What we call the Moho today may not have existed 100 million years ago, and what we measure tomorrow may already be shifting beneath us. It is a moving threshold, one that reflects the living nature of the Earth itself. There is something profoundly humbling in that realization. To study the Moho is to accept that the Earth is not static but breathing, and that its boundaries are not fixed lines but evolving states of being. When scientists listen to the echoes that return from the depths, they are not merely mapping rock, they are tracing the rhythms of a planet that has never ceased to transform. Beneath the Moho, the composition of the Earth changes in ways that defy ordinary perception. The rocks that make up the mantle are not like those familiar to the surface, they are dense, compacted, and crystalline, forged under pressures that would crush any human-made structure. Here, in the uppermost mantle, lies a material known as peridotite, a greenish, coarse-grained rock rich in olivine and pyroxene. It is a mineralogical landscape of endurance, one that has existed, unaltered in essence, since the planet's earliest days. While the crust fractures, folds, and erodes, the mantle persists, its slow motions measured not in years or centuries but in cycles of deep time that stretch across millions of years. The upper mantle does not flow in the way that water flows, nor is it solid in the way that stone is solid. It occupies a state that seems paradoxical to human understanding, both rigid and capable of slow, creeping movement. This is the realm of ductile deformation, where rock can bend and flow given enough time and heat. The energy that drives this slow motion arises from the Earth's core, from the decay of radioactive elements and the residual heat of formation. Over eons, this heat radiates outward, causing convection currents that move material upward and downward in vast, sluggish loops. The Moho marks the surface of this movement, the skin that separates the world of shifting, molten flow from the brittle plates that ride above it. Scientists have come to understand that the mantle's behavior governs the very architecture of the surface world. Every mountain, every ocean basin, every continent owes its existence to the unseen motions of the mantle below. Where hot material rises, crust is stretched and new seafloor is born. Where it sinks, old crust is consumed and recycled. These vast circulations are the breath of the planet, though they move too slowly for human senses to register. The average rate of mantle flow is measured in centimeters per year, roughly the rate at which fingernails grow. And yet, over geological time, this imperceptible motion reshapes continents, builds mountain ranges, and closes entire oceans. At certain depths within the mantle, the minerals themselves begin to transform. Under immense pressure, olivine rearranges its atomic structure, becoming denser and more compact. These transitions occur in stages, each corresponding to a different layer within the mantle. The first transformation, around 410 kilometers deep, marks the change from olivine to a mineral known as wadsleyite. Deeper still, at around 520 kilometers, wadsleyite becomes ringwoodite. Each of these transitions alters how seismic waves travel through the planet, producing faint echoes that scientists can detect. These subtle shifts reveal that the mantle is not homogeneous, but a complex, layered environment where temperature and pressure sculpt the very structure of matter. One of the most fascinating discoveries of recent decades is that the mantle is not entirely dry. For many years, geologists assumed that the deep Earth was devoid of water, but evidence from inclusions in ringwoodite crystals has suggested otherwise. Tiny pockets of water, trapped as hydroxyl ions within the crystal lattice, hint that the mantle may hold as much water as all the oceans combined, though not in liquid form. This hidden reservoir plays a quiet but crucial role in the planet's evolution. Water lowers the melting point of rock, influences the generation of magma, and helps drive volcanic activity at the surface. In a sense, the oceans above and the mantle below are connected through this deep hydrological cycle, an invisible dialogue between surface and interior. When viewed through the lens of seismic imaging, the mantle appears as a world of constant motion. Hot plumes rise from deep within, sometimes reaching the base of the crust to create volcanic hotspots such as those that formed the Hawaiian Islands. In other regions, slabs of cold oceanic crust descend into the mantle at subduction zones, where they are slowly assimilated and melted. These descending slabs penetrate deep, carrying with them traces of the surface, sediments, water, and even bits of the biosphere, down into the planet's interior. The mantle, then, is not a static layer but a dynamic system of recycling and renewal, in which surface material is continuously reincorporated into the deep earth and re-emerges millions of years later in new form. The temperature gradient within the mantle is immense, rising from roughly 500 degrees Celsius near the Moho to more than 3,000 degrees near the core mantle boundary. Yet because the pressure increases so dramatically with depth, much of the mantle remains solid. The heat does not manifest as molten rock except in regions where conditions allow partial melting, beneath mid-ocean ridges or volcanic arcs, for example. In those places, magma forms and migrates upward, feeding eruptions that renew the crust and release gases into the atmosphere. The Moho acts as a kind of filter in this process. Below it, the mantle convects and melts. Above it, the crust fractures and vents. The interaction between the two defines the dynamic equilibrium of the Earth's surface. In the stillness of geological time, the mantle's motion might be compared to the slow turning of a vast wheel. Material sinks, heats, and rises again, tracing patterns that span the entire globe. Computer models of this convection suggest that the circulation of the mantle may be organized into large cells, some of which may persist for hundreds of millions of years. Within these currents, elements mix and differentiate, giving rise to the chemical diversity of volcanic rocks we find at the surface. Even the continents themselves, buoyant and ancient, drift upon this slow tide, carried by the unseen machinery of the mantle's flow. The idea that something so immense could move so gently invites a kind of reverence. It challenges the human sense of scale, reminding us that even the hardest stone is fluid when given enough time. The mantle does not hurry, does not pause, it moves in accordance with the quiet laws of physics and thermodynamics. Heat, pressure, and density determine its rhythm, and in that rhythm, the Earth maintains its balance. To contemplate this is to glimpse the planet as a living organism, not alive in the biological sense, but alive in motion, in exchange, in persistence. And so the Moho, far from being merely a geological boundary, becomes a symbol of that living process. It is the membrane through which the energy of the deep interior communicates with the fragile crust above. It is the place where the slow breath of the mantle touches the world we know, the threshold between what we can observe and what we can only imagine. Above it lies the familiar domain of rock, ocean, and atmosphere, below it, the vast, churning deep that sustains them all. To stand upon the surface of the Earth, anywhere on the globe, is to stand upon that invisible conversation, that patient exchange of heat and motion that has continued for more than 4 billion years. Deeper still, beyond the range where surface analogies begin to fail, the mantle gives way to a region that scientists call the transition zone. This is the realm between approximately 400 and 1,000 kilometers beneath the surface, where minerals continue to rearrange themselves into denser and more compact forms. The atoms here are pressed together so tightly that the ordinary structure of minerals begins to collapse, giving rise to new, exotic arrangements that can only exist under such conditions. It is in this quiet, crushing darkness that the Earth begins to take on a different personality, no longer behaving like the rock of the surface, nor yet like the molten metal of the core. In the transition zone, pressures exceed 13 gigapascals, more than 100,000 times the atmospheric pressure at sea level, and the temperatures climb past 1500 degrees Celsius. Under these conditions, the boundaries between solid and liquid begin to blur. Seismic waves traveling through this region move faster or slower depending on subtle variations in composition, temperature, and phase. To the trained eye of a seismologist, these changes appear as faint reflections, the signatures of hidden structures. Each signal tells a story about how the Earth breathes heat from its core outward and how that heat moves through the deep. Somewhere within this zone, perhaps near its lower boundary, lies one of the most intriguing mysteries in modern geology, the origin of deep mantle plumes. These are vast upwellings of hot material that rise from the depths like underwater geysers, moving slowly toward the surface. When they reach the base of the lithosphere, they can create volcanic hotspots, places like Hawaii, Iceland, and Réunion, where molten rock wells up through the crust in a steady, unending rhythm. The plumes may begin at the boundary between the mantle and the core, nearly 3,000 kilometers below our feet, carrying heat and material from the deepest interior toward the surface. In a sense, they are the Earth's slow heartbeat, the steady pulse that renews the crust and stirs the chemistry of the oceans and atmosphere above. Below the transition zone lies the lower mantle, a domain that extends to a depth of about 2,900 kilometers. This layer makes up more than half the volume of the entire planet, and yet it is perhaps the least understood. The pressures here are so immense that laboratory experiments struggle to reproduce them. The materials behave in ways that challenge even the most advanced models. Scientists believe the lower mantle is composed primarily of a mineral called bridgmanite, named after the physicist Percy Bridgman, who pioneered the study of materials under extreme pressure. Bridgmanite is extraordinarily stable, capable of maintaining its structure across a vast range of temperatures and pressures. It is, in many ways, the quiet foundation of the planet's solidity. But even here, where everything seems motionless, there are signs of movement. Convection currents continue, though they are slower and broader than those in the upper mantle. The flow here may span thousands of kilometers, taking hundreds of millions of years to complete a single cycle. Some regions appear hotter and less dense, perhaps connected to the rising plumes that feed volcanoes. Others are cooler and denser, where ancient slabs of subducted crust may have sunk and become trapped. The lower mantle is a vast, slow-moving sea of rock, dense enough to transmit seismic waves as if through metal, yet still capable of shifting and folding on scales beyond comprehension. It is within this lower mantle that the concept of deep time becomes almost tangible. The materials here have circulated since the earliest history of the Earth, long before the first oceans formed or the continents drifted into their familiar shapes. They have witnessed the assembly and breakup of supercontinents, the rise and fall of mountain ranges, the slow drift of magnetic poles. Every cycle of convection, every plume that rises or slab that sinks, contributes to the planet's evolution as surely as erosion shapes a coastline. The difference is only one of scale. What happens here unfolds over spans of time so great that human history vanishes into insignificance beside it. As we descend toward the boundary between the mantle and the core, the conditions become almost unimaginable. Temperatures rise to nearly 4,000 degrees Celsius, and pressures approach 135 gigapascals. At this depth, we reach what scientists call the D-double-prime layer, a narrow but complex region where the solid silicates of the mantle interact with the molten metals of the outer core. This boundary is neither smooth nor static. It is a landscape of thermal anomalies, chemical heterogeneity, and strange seismic behavior. Some areas appear to contain enormous reservoirs of partially melted rock, while others are dominated by solid, ultra-dense material that may represent remnants of the planet's early differentiation. These heterogeneities are known as large low-shear velocity provinces, or LLSVPs. They are massive structures, each the size of a continent, lying deep beneath Africa and the Pacific Ocean. Seismic studies reveal that waves slow dramatically as they pass through these regions, suggesting differences in temperature, composition, or both. Some scientists believe the LLSVPs may be the roots of mantle plumes, others think they are relics from the planet's formation, fragments of primordial material that have persisted for billions of years. Whatever their nature, they stand as silent witnesses to the deep history of the Earth, holding secrets that no instrument has yet fully decoded. Just above the core mantle boundary, there are hints of even stranger phenomena. Experiments and simulations suggest that minerals here may undergo chemical reactions with the liquid iron of the core, producing exotic compounds that alter the dynamics of heat transfer. In some places, the boundary may be eroding slowly, as core material mixes upward into the mantle. In others, mantle material may sink downward, cooling the outer core and influencing the generation of Earth's magnetic field. This delicate balance, between solid and liquid, between rock and metal, defines the inner workings of the planet in ways that extend all the way to the surface. The heat that escapes from the core through this boundary powers the mantle's convection, and in turn, drives the motion of tectonic plates. The continents drift because the core radiates warmth into the rock above it. Volcanoes erupt because that warmth melts pockets of material along the way. Even the oceans and atmosphere owe their existence, indirectly, to this deep transfer of energy. It is humbling to realize that every breeze, every current, every drop of rain is connected, in some subtle way, to the vast and silent processes unfolding thousands of kilometers below. If one could somehow stand at the base of the mantle, at the boundary of the core, the experience would be beyond comprehension. The rock would not feel like rock, it would flow like pitch, glowing with internal heat. The pressure would be so immense that even atoms would be forced into proximity, their electrons shifting into new configurations. There would be no sound, only the vibration of the planet itself, an endless resonance that began with its birth and will continue until it cools and stills into silence. Below the mantle, the nature of the Earth changes completely. The solid rock that defines all the layers above gives way to something fluid, metallic, and alive with motion. Here begins the outer core, a sphere of molten iron and nickel extending from about 2,900 kilometers beneath our feet to roughly 5,100 kilometers. The pressure here is nearly 1.5 million times what we feel at the surface, and yet, in spite of such compression, the temperature, exceeding 4,000 degrees Celsius, keeps the metals in a liquid state. This is a realm of perpetual motion, a churning ocean of molten metal circulating under forces so vast that they generate one of the most remarkable features of our planet, the magnetic field. If the mantle can be thought of as the lungs of the planet, breathing heat in slow cycles, then the outer core is its beating heart. Convection currents move through the molten iron in colossal loops, hot material rises from the boundary with the inner core, cools as it approaches the mantle, then sinks again, creating endless, self-sustaining circulation. The movement of this conductive liquid, combined with the planet's rotation, gives rise to the geodynamo, the process through which the Earth's magnetic field is born. The geodynamo is one of nature's most intricate and elegant mechanisms. In essence, as the molten metal flows, it generates electrical currents. These currents, in turn, create magnetic fields. Those fields reinforce the flow itself, shaping the motion of the metal into spiraling columns that align with the planet's rotation. It is a feedback loop of immense stability and power, sustained by the slow release of heat from the inner core and the gradual crystallization of iron deep within. To imagine this motion is to imagine a kind of metallic weather, a vast, liquid storm system unfolding beneath the mantle, far more energetic than any hurricane or current on the surface. The flows are immense, thousands of kilometers across, but slow, creeping perhaps a few tens of kilometers per year. Yet even such small velocities, multiplied by the sheer density of the material and the scale of the domain, produce magnetic fields strong enough to reach through the mantle, across the crust, and far out into space. It is because of this hidden motion that compass needles align, that migratory birds can navigate across oceans, and that our planet is shielded from cosmic radiation. The magnetic field acts as a vast, invisible shield, deflecting charged particles from the sun and shaping the auroras that dance across polar skies. Every flicker of light in the northern and southern lights is, in a sense, an echo of the boiling, shifting currents deep within the Earth's metallic heart. The heat driving this movement comes from two primary sources. Some of it is primordial, the residual warmth from the Earth's violent formation, when countless planetesimals collided and coalesced into a single, molten sphere. But much of it comes from the gradual crystallization of the inner core. As the inner core solidifies, iron separates from the surrounding liquid, releasing latent heat and lighter elements like sulfur and oxygen. These lighter elements rise, setting the molten metal into motion. Thus, the inner core acts not only as a growing solid center but also as the engine that keeps the outer core flowing. Though we cannot see the outer core directly, seismic waves allow us to map its properties with surprising precision. When large earthquakes send vibrations through the planet, the waves travel at different speeds depending on what they move through. P waves, or primary waves, can pass through both solids and liquids, but S waves, secondary waves, cannot travel through liquids at all. By observing which seismic waves disappear and where they reappear, scientists have traced the boundary between the solid mantle and the liquid core with remarkable accuracy. It was through this method, in 1906, that the British seismologist Richard Dixon Oldham first discovered the existence of the outer core, a hidden ocean of molten metal no human eye would ever see. Within this ocean, strange patterns seem to emerge. Seismic studies and computer models suggest that parts of the outer core may flow faster than others, forming enormous gyres that drift slowly around the inner core. Some regions may be more turbulent, while others remain relatively stable. There are hints that these differences could influence the magnetic field above, contributing to its gradual drift and occasional reversal. Every few 100,000 years, the field weakens, then flips entirely, with magnetic north becoming south and vice versa. During these reversals, the Earth's magnetic strength may drop to a fraction of its usual power, allowing more cosmic radiation to reach the upper atmosphere. Yet life persists through it all, and the field eventually stabilizes again, as if the heart of the planet simply resets its rhythm. The outer core, though dynamic, is remarkably consistent in its composition. Roughly 85% of it is iron, with most of the remainder being nickel and trace amounts of lighter elements. The density of this molten mixture is about 10 times that of water, so a single cubic meter of it would weigh as much as 10 small cars. The heat and pressure cause the atoms to move like an ultradense fluid, where viscosity is low but momentum is immense. If one could somehow dip a hand into it, which, of course, no living thing ever could, it would feel more like liquid mercury than lava, flowing freely but with a strange, metallic weight. At the lower boundary of this layer lies the inner core, a sphere about 1,220 kilometers in radius, composed primarily of solid iron and nickel. It is here that the conditions finally become too extreme for even metal to remain molten. The pressure at this depth, around 3.5 million times atmospheric pressure, forces the atoms into a crystalline structure, freezing the iron despite temperatures exceeding 5,000 degrees Celsius. It is a paradoxical world, where the hottest place on Earth is also one of its most solid. The discovery of the inner core came later, in 1936, through the work of Danish seismologist Inge Lehmann. She noticed that certain seismic waves, which should have been blocked by the liquid outer core, were reappearing on the opposite side of the planet. The only explanation was that they were refracting through a smaller, solid sphere at the center, a finding that revolutionized our understanding of the Earth's interior. In many ways, the inner core is a planet within a planet. It rotates independently of the mantle and crust, spinning slightly faster or slower over time. Studies suggest it may complete one extra rotation relative to the surface every few centuries. This differential motion likely affects the outer core's flow, which in turn influences the magnetic field. The entire system is an intricate dance of heat, pressure, and motion, maintained through balances so precise that even slight shifts can ripple outward across geological time. And yet, despite its stability, the inner core is not perfectly uniform. Recent research hints that it may have layers of its own, a boundary within the boundary. Some seismic waves travel faster along certain directions, suggesting that the crystalline structure is aligned or even divided into distinct zones. At the very center, a region less than 400 kilometers across, there may exist an innermost inner core, with a different crystal orientation, perhaps recording the earliest phase of the planet's solidification. It is a strange thought, that the deepest structure of the Earth may contain within it a record of its own growth, written in the slow freezing of metal over billions of years. As the inner core continues to solidify, the planet's heart slowly expands while the outer core thins. This process will continue for billions of years more, gradually cooling the Earth from within. Long after the continents have shifted into new configurations, long after the last mountains have eroded into dust, the inner core will still be growing, atom by atom, crystallizing its story in silence. The heat from the core rises upward in waves of slow, patient movement, seeping through the viscous mantle in convection cells that operate on a timescale beyond all human reckoning. Each loop of molten rock, ascending, cooling, and descending again, can take tens of millions of years to complete a single cycle. It is through this unending motion that the deep interior of the planet transfers its energy outward, shaping the world above in quiet, persistent ways. Where these convection currents meet the underside of the crust, the energy must find release. It does so through fractures, fissures, and zones of weakness, where magma can seep upward and solidify to form new rock. The most visible of these places are the mid-ocean ridges, vast, continuous mountain chains that stretch like seams along the ocean floor. Here, the mantle slowly pulls apart, and new crust emerges from the spreading centers. The process is so slow that it seems still to us, just a few centimeters per year, but over geological time it builds entire oceans, rearranges continents, and redefines the shape of the Earth. The crust that forms at these ridges is young, fresh, and dense. Composed mainly of basalt, it carries the magnetic imprint of the planet's field at the moment it cools. Over millions of years, as magma emerges and solidifies symmetrically on both sides of a ridge, it records the history of magnetic reversals like a barcode of time. Each stripe of basalt, alternating in magnetic polarity, tells of epochs when north became south and then north again, frozen proof of the restless field born in the molten core below. As this oceanic crust moves away from the ridges, it cools and thickens, eventually descending into the deep ocean basins. But its journey does not end there. Along the edges of continents or deep trenches, it bends downward and plunges back into the mantle in a process known as subduction. Here, the oceanic plate, cold, dense, and heavy, sinks beneath lighter continental rock, melting and releasing fluids that trigger volcanism above. Thus, mountains rise and earthquakes rumble as the planet recycles its outer skin. Every subduction zone marks a place where the surface is folded back into the depths, where old crust returns to its origin in the mantle and is reborn as molten material once again. The cycle of creation and destruction, spreading and subduction, defines the slow breathing of the Earth. The Moho, that subtle discontinuity between crust and mantle, is the interface through which this breath passes. It is where the rigid lithosphere meets the ductile asthenosphere, where the brittle skin of the planet rests upon the slow-moving fluid below. Through the Moho, stresses accumulate and release, sometimes violently, in the form of earthquakes. But mostly, the movement is silent, imperceptible, steady. In the deepest subduction zones, where old oceanic crust descends, the Moho bends and folds with it, creating structures that defy easy mapping. Sometimes it thickens, sometimes it breaks. In continental regions, especially those shaped by mountain building, the Moho can lie 60 or 70 kilometers beneath the surface, distorted by the enormous weight of rock above. In contrast, under young oceanic crust, it may be found at barely 5 kilometers depth. The Moho is not a simple shell, but a surface that flexes and shifts with the living dynamics of the Earth's interior. To imagine it, one might picture a delicate boundary film, invisible yet fundamental, separating two realms of utterly different character. Above it, the crust is cool, brittle, and filled with the minerals that form our continents and ocean floors, granite, basalt, and sedimentary layers built by erosion and time. Below it, the mantle begins, hot, dense, and viscous, its minerals rearranged into high-pressure forms such as olivine and pyroxene. The difference between the two is both physical and chemical. Yet what makes the Moho remarkable is that it is not a sharp line but a transition zone, a gradient through which the properties of matter slowly change. Seismic waves, again, are our primary tool for tracing this hidden interface. When earthquakes send their energy through the crust, part of the wave reflects off the Moho while another part refracts and travels through the mantle. By recording the travel times and amplitudes of these waves at different stations, scientists can model the depth and shape of the discontinuity. Across continents, the data reveal patterns of thick crust beneath mountains, thinner crust beneath rift zones, and complex variations beneath ancient shields and basins. Yet even now, despite decades of seismic research, we have never physically reached the Moho. Every attempt to drill through the crust to that boundary has ended in failure, defeated by the hardness of rock, the cost of deep drilling, and the unpredictable heat and pressure at depth. The most famous effort, known as Project Moho, began in the 1960s off the coast of Mexico. It succeeded in penetrating only about 180 meters into the oceanic crust before being abandoned. Later, the Soviet Union's Kola super-deep borehole reached a depth of 12 kilometers, by far the deepest hole ever drilled, but even that achieved only about a third of the way to the Moho in continental rock. At those depths, the conditions were extreme. The rock temperature exceeded 180 degrees Celsius, and the drill bits wore out faster than they could be replaced. Engineers reported that the rock itself began to behave strangely, becoming plastic and less cooperative with the machinery. The sound from the borehole, low, resonant, almost metallic, was said to have unnerved even seasoned geologists. Beyond that depth, progress slowed to a crawl. Eventually, the project was halted, not because of lack of will, but because the materials and technology of the time simply could not endure. And so, the Moho remains unconquered, a frontier that exists just beyond our reach. We can describe its seismic signature, model its variations, even infer its composition, but no human instrument has ever touched it. It is, in a very real sense, the last unmapped border within our planet. Every meter we descend brings new challenges: heat, pressure, instability, and the limits of endurance. Yet this unreachability gives the Moho a certain dignity, a quiet reminder that some boundaries, though physically close, remain conceptually distant. It is humbling to realize that we have sent machines to the edge of the solar system, yet cannot touch the layer beneath our own feet. The crust beneath the oceans may be thinner than a fingernail compared to the planet's size, and still, it eludes our direct exploration. But perhaps that is fitting. The Moho was never meant to be a place of conquest. It is the silent interface that binds the solid world we know to the deep engine below, a reminder that the ground we stand upon is only a skin, thin, fragile, and forever shifting atop a sea of stone that moves like a dream. Over immense spans of time, the heat rising from the mantle weaves patterns of transformation across the crust. It rises not in sudden bursts but in languid waves of energy, spreading outward and upward through fractures invisible to the surface eye. This movement, slow beyond comprehension, carries with it the raw potential for both destruction and creation. It is the quiet pulse of the planet's metabolism, the same deep rhythm that has shaped mountains, opened seas, and rearranged the continents in their endless drift. Each plume of heat, each slow convective roll of the mantle, finds its own way to express the planet's interior restlessness. Some rise beneath spreading ridges, where two plates move apart, allowing the molten material to well up and form new ocean floor. Others gather beneath continental crust, where the heat becomes trapped, softening the lower layers until they begin to flow like thick wax. It is this gentle movement that can raise entire mountain ranges over millions of years, buckling and folding the lithosphere in long arcs that leave behind chains of peaks stretching across whole continents. There is a kind of poetry in this invisible motion, an elegance that belies its violence. The mountains we see today, their summits wrapped in clouds, are the surface expression of slow collisions that began before our species existed. Beneath them, the Moho is compressed and thickened, pressed downward by the weight above, its boundary pushed deeper into the mantle. Seismic studies have revealed that beneath great ranges like the Himalayas, the Moho dips as far as 70 kilometers, a graceful sag in the architecture of the planet, shaped by forces that move too slowly for us to feel. And yet, even as mountains rise, the crust elsewhere is being consumed. Along deep oceanic trenches, the Earth folds in upon itself. The oceanic plate, having cooled and thickened since its birth at a ridge, now grows too dense to remain afloat. It bends downward, sliding beneath the lighter continental plate in a slow, silent dive into the mantle. The descent is neither uniform nor smooth, it grinds, fractures, and resists, storing immense tension until it suddenly releases in the form of earthquakes. Each tremor, though fleeting, is a reminder of the invisible forces constantly reshaping the Earth's face. As the plate sinks deeper, it carries with it water, sediments, and fragments of the crust, all of which are gradually transformed by the increasing pressure and heat. The trapped water, forced from the descending rock, rises into the overlying mantle wedge, lowering its melting point and allowing magma to form. That molten material, lighter than the rock around it, ascends through cracks and weaknesses, feeding volcanic arcs that mark the edge of subduction zones. In this way, the crust is both destroyed and renewed, consumed in one place and reborn in another, in a cycle that has continued for hundreds of millions of years. The Moho, caught within this cycle, is not a fixed surface but a living boundary, flexing, melting, and reforming as plates shift. Beneath subduction zones, it may disappear entirely, replaced by complex layers of intermixed materials, part crust and part mantle, indistinguishable from one another. Beneath spreading ridges, it may be newly created, a thin, distinct interface between the fresh basalt above and the hot peridotite below. Everywhere, it moves at the same slow pace as the continents, tracing a story of endless adjustment and renewal. The materials that make up this hidden world are strange and beautiful in their resilience. The mantle's dominant mineral, olivine, glows green in its pure form, but deep within the earth, under pressures that would crush steel, its structure transforms into denser arrangements, first wadsleyite, then ringwoodite, each phase marking a deeper layer in the planet's anatomy. These transitions occur far below the Moho, yet they echo the same principle, that matter, when subjected to the quiet insistence of time and pressure, reorganizes itself into more stable forms. At the boundary itself, the change is chemical as much as structural. The rocks above are rich in aluminum and silicon, those below contain more iron and magnesium. Between them lies a narrow zone where these elements mix, reacting under the influence of temperature and stress. It is there that the sound waves of earthquakes bend and refract, revealing the subtle difference between crust and mantle. In that narrow band, 1 billion years of geological history is recorded in silence. Though the Moho cannot be touched, its presence is felt through instruments that capture the echoes of the planet's inner life. Seismometers, spaced across continents and anchored to the seafloor, record the passing of waves that ripple through the earth after each quake. By comparing the times at which those waves arrive at different stations, geophysicists can build a picture of the structure beneath. They map the Moho as a surface of contrasts, an unseen mirror reflecting the motion of energy through stone. But even with all our measurements, we know less than we might wish. The exact composition of the rocks at the boundary remains uncertain. Some models suggest a thin layer of partially melted material, a kind of magmatic lubricant that allows the crust to move more freely over the mantle. Others imagine a gradual intermingling of elements, a spectrum rather than a line. The truth, hidden beneath kilometers of rock, may be more complex still, involving processes we have not yet imagined. The inaccessibility of the Moho has made it a kind of legend among geologists, a symbol of the limits of human curiosity. The name itself carries an aura of reverence. To speak of it is to acknowledge the divide between what we can observe and what we can only infer. And yet, this very limitation is what fuels our fascination. The Moho reminds us that knowledge is not a destination but a journey inward, one that mirrors the slow descent of seismic waves and the patient drift of continents. Perhaps it is fitting that this boundary remains untouchable. The more we seek it, the more it seems to recede, not because it hides itself, but because the act of seeking reveals new depths we had not known to exist. Just as the horizon moves farther away as we approach it, the Moho is a frontier that forever remains ahead of us, urging us to listen more closely to the murmurs of the planet. Beneath the continents, the story grows more intricate. The crust here is older, thicker, and infinitely more complex than the young, cleanly formed crust beneath the oceans. It is a layered archive, a record of ancient collisions, rifts, and buried oceans, folded upon itself through eons of pressure. Within it, the Moho lies deeper, hidden beneath mountain roots and continental shields that have endured for billions of years. To peer beneath such regions is to glimpse the very architecture of stability, the structures that have anchored the continents in their long drift across the mantle's restless surface. If the oceanic Moho is youthful and sharp, the continental Moho is aged and blurred. In some places, it is not a single boundary at all but a transition spread across several kilometers. This complexity arises because the continental crust has been built, destroyed, and rebuilt countless times. Fragments of ocean floor have been thrust upward, volcanic arcs welded onto old cratons, and sedimentary layers buried deep enough to metamorphose into new rock. Each addition leaves behind traces, chemical, structural, and seismic, that complicate the signal of the Moho. What was once a crisp acoustic reflection becomes a diffuse region of echoes, like whispers overlapping in a vast underground hall. Scientists often describe the continental crust as buoyant, floating atop the denser mantle like an iceberg in water. But this image, while poetic, hides a profound truth. The continents do not simply rest upon the mantle, they root into it. Beneath the towering peaks of mountain ranges, the crust thickens downward to compensate for the weight above, forming deep keels that extend far below the surface. These roots, composed of ancient metamorphic rock, are part of why mountains persist. Without them, gravity would have long since worn the peaks flat. The Moho, in these regions, lies buried beneath layers of rock that have been compressed and metamorphosed until they resemble the mantle itself. In the deep roots of continents, heat moves sluggishly. The rocks are poor conductors, and the thick crust acts as a blanket, trapping the warmth that seeps upward from the mantle. This heat flow, though gentle, exerts a quiet influence. Over immense spans of time, it can weaken the lower crust, making it capable of slow, ductile flow. It is in these depths that orogenic belts, the buried scars of mountain building, soften and spread, their once sharp structures relaxing into broad, gentle domes. The Moho, too, responds to these shifts, rising or sinking in tune with the long breathing of the earth. When we speak of the continents moving, we often imagine them sliding as rigid rafts across the surface of the planet. But the truth is subtler. The continents deform as they move, they bend, crack, and flex like living tissue. The Moho beneath them is part of that motion, a dynamic surface that accommodates the stresses imposed by the slow ballet of plate tectonics. It tilts beneath subduction zones, warps beneath rift valleys, and ripples beneath colliding continents. The seismic reflections from these regions tell stories of distortion and resilience, a geological language written in echoes. Modern techniques, such as seismic tomography, have given us the ability to see these variations in 3 dimensions. By compiling vast datasets of earthquake waves recorded around the globe, scientists can construct images of the Earth's interior that resemble medical scans. In these images, the Moho appears not as a line, but as a textured surface, undulating and folded. Under young mountain belts like the Andes, it dips steeply. Beneath ancient shields like those of Canada or Africa, it lies deep and even, a testament to long stability. Each contour tells a story of formation, collision, and repose. There are places, too, where the Moho may be missing, or at least transformed beyond recognition. In rift zones, where the crust is being pulled apart, the boundary becomes shallower and more diffuse. Hot mantle material wells upward, thinning the crust and replacing it with new basaltic rock. Over time, these regions may evolve into new ocean basins, and what was once continental Moho becomes oceanic. Thus, even the identity of the boundary shifts through geological time, its nature as transient as the continents it supports. The notion that the Moho is a discontinuity can be misleading. It suggests a sharp break, but in many regions it behaves more like a threshold, a zone of transition from brittle to ductile behavior, from felsic to mafic chemistry, from static to flowing energy. Across this threshold, the physics of matter itself change. Rocks above it fracture under stress, those below it flow. The difference is not only one of composition but of behavior, a fundamental shift in how the Earth's materials respond to pressure, temperature, and time. This behavioral boundary is part of what makes the Moho so fascinating. It marks the limit of our direct experience of solid ground. Everything above it, we can reach, drill, or measure. Everything below it belongs to a world governed by other rules. In that deep world, solid rock moves like a fluid, and time stretches into scales that dissolve our normal sense of duration. It is, quite literally, the threshold between the human and the geological, between what we can grasp and what we must imagine. If one could descend through the crust toward the Moho, the journey would not be abrupt. The familiar rocks of the surface, granite, sandstone, and basalt, would gradually give way to denser and darker materials. The air would vanish, replaced by rock that creaks under its own weight. Temperatures would rise by about 25 degrees Celsius per kilometer, and pressure would increase by hundreds of atmospheres with every step downward. By the time the boundary approached, the rocks would glow with internal heat, their minerals beginning to deform plastically. There would be no line to cross, no visible boundary, only the slow realization that the behavior of matter had changed. It is a sobering thought that this transformation happens just a few tens of kilometers below our feet. On a planetary scale, it is almost nothing, less than the thickness of an eggshell compared to the whole Earth. Yet within that narrow space lies the key to understanding the forces that shape continents, trigger earthquakes, and build mountains. The Moho is both boundary and bridge, both separator and connector. It is the interface through which the deep interior of the planet communicates with the world above, transmitting its heat, its motion, and its long, patient will. Through the Moho, energy from the planet's interior rises in forms both violent and invisible. It is here that the slow convection of the mantle translates into the tremor of an earthquake, the uplift of a mountain, or the quiet accumulation of strain that one day releases as catastrophe. The crust above may appear static to us, yet it is in constant negotiation with the world beneath. Every motion, every drift of a continent or rift of a valley, begins as a whisper below that boundary, a signal in rock that takes centuries to reach the surface. In this way, the Moho becomes not merely a line between layers but a living membrane, through which the deep earth breathes and exerts its will. Heat seeps upward through this boundary like memory rising through sleep. In some regions, this heat is subtle, a mere trickle of thermal energy, enough to soften the rocks of the lower crust. In others, where the mantle pushes close to the surface, it bursts through as volcanic fire. Beneath Iceland, beneath Hawaii, beneath the East African rift, the Moho glows with molten promise. Mantle plumes, columns of hot material rising from the depths, thin the crust and feed magma chambers. There, the separation between crust and mantle becomes blurred, replaced by a seething mixture of melt and crystal. It is from such places that new land is born. If the continents represent the memory of Earth, the Moho is its pulse. Every mountain that rises above the horizon, every ocean trench that plunges into shadow, owes its shape to forces that move through that boundary. In subduction zones, the crust dives beneath another plate and carries with it the sediment of ages. As it sinks, it crosses the Moho in reverse, transforming from crust to mantle once more. Rocks that were once part of continents are dragged into the deep, heated, melted, and reincarnated. The boundary, in this sense, is not permanent. It is a cycle, a breathing edge that expands and contracts with time. Imagine standing on a quiet plain, the ground unmoving beneath your feet. You feel nothing of the slow dance happening below, yet beneath the calm, kilometers of rock flex and bend. Stress builds along faults, pressure rises in magma chambers, and heat diffuses upward like the slow exhalation of a sleeping giant. The Moho sits beneath all this, absorbing and transmitting the planet's internal rhythms. When an earthquake shakes a city, when a volcano carves a new island from the sea, it is this deep surface that has whispered first. It is the hand behind the motion, unseen but eternal. Seismologists, who study how the earth quivers, have learned to listen to the Moho's voice. They send waves into the ground and listen for the echoes that return. These echoes are faint, mere fractions of a second in delay, but they tell of depths beyond imagining. When those echoes arrive, they reveal the subtle differences between regions. Some parts of the boundary reflect sound sharply, like glass, others absorb it, like cloth. This variation speaks of temperature, composition, and pressure. From such whispers, entire maps of the deep earth are drawn, landscapes that no eye will ever see, but that shape the surface we inhabit. In the last few decades, scientists have learned to combine seismic data with gravitational and magnetic measurements to create fuller images of what lies below. The Moho emerges from this synthesis as something dynamic, warped, stretched, uplifted. Under mountain ranges, it bows downward, holding the mass above in balance. Under ocean basins, it rises closer to the surface, thinned by the pull of spreading ridges. This interplay between surface and depth is delicate but constant. The crust floats upon the mantle not in stillness but in perpetual adjustment. Every erosion, every glacier, every flood alters the weight pressing downward, and the Moho responds by rising or sinking, keeping equilibrium in ways too slow for human senses to perceive. What this means is that the Earth's surface, though appearing solid, is in conversation with its depths. The mountains that erode today lighten the crust, allowing it to rise slightly higher over thousands of years, a process called isostatic rebound. Likewise, when new sediment accumulates in deltas or ocean basins, the crust sinks ever so slightly to make room. These movements ripple through the Moho, like tension traveling through the skin of a drum. Over geologic time, this flexing alters coastlines, river paths, and even the direction of mountain building. The boundary, then, is not passive, it is a responsive, adjusting interface that mirrors the life above it. Some researchers now suspect that much of the planet's deep chemistry, the cycling of elements that sustain the biosphere, is influenced by exchanges across the Moho. Water and carbon, drawn into the mantle at subduction zones, return through volcanic outgassing. The same processes that build continents and oceans also regulate the composition of the atmosphere. In this way, the Moho stands at the crossroads of geology and biology, connecting the fate of mountains and microbes. Without it, the planet's heat would not circulate, continents would not drift, and the long cycle of renewal that keeps Earth alive would fall still. And yet, for all our understanding, the Moho remains beyond direct reach. The deepest boreholes have only grazed a third of the way to it. Technology falters against the crushing pressures and immense heat. It is a boundary that resists intrusion, not by malice, but by scale. To touch it would be to meet the ancient heart of the planet, the silent machinery that sustains motion and form. Perhaps that is why it fascinates us. It is near enough to imagine, but far enough to remain mythic. In the end, the Moho is not simply a geological feature. It is the symbol of limit, the point at which our tools, our senses, and even our concepts strain against the vastness of the world we inhabit. It reminds us that the Earth, for all our knowledge, still holds regions of deep mystery. Every tremor, every mountain, every quiet shift beneath our feet speaks its name. It is not a line in rock but a whisper in time, the slow heartbeat of a living planet, pulsing beneath us all. Beneath the Moho, the world softens into motion. The mantle, though solid in form, moves with the patience of eternity, a slow circulation of rock that behaves like liquid when given time enough to flow. It is a vast ocean of silicate minerals, stretching from the base of the crust to nearly 3,000 kilometers down, where it meets the liquid outer core. Here, temperature and pressure rewrite the rules of matter. Rock no longer fractures as it would near the surface, instead, it bends, deforms, and creeps with the unhurried grace of glaciers. Each mineral grain, each crystal lattice, is engaged in an imperceptible migration, exchanging positions with its neighbors as heat seeps upward from the core and cold drifts downward from the crust above. This cycle is the slow breathing of the planet, convection on a scale that dwarfs imagination. Columns of hot, buoyant rock rise through the mantle, spreading beneath the crust like invisible currents. As they cool, they sink again in faraway trenches, completing loops that can take hundreds of millions of years. Through these motions, continents are carried, oceans opened and closed, and mountains raised from what was once seafloor. The surface of the Earth, restless and shifting though it may seem, is but the outer film of this greater circulation. When we trace the drift of tectonic plates, we are watching the mantle's breath. Where the mantle rises, the Moho thins, drawn upward by the warmth below. Basaltic magma forms as pressure drops, erupting along mid-ocean ridges in endless, silent chains. There, the crust is born anew, thin, dark, and young, stretching away from the ridge like the cooling skin of the planet. In contrast, where the mantle sinks, it drags oceanic crust down with it, returning it to the depths from which it came. This dance of creation and destruction defines the geology of our world. Every pebble, every grain of sand, is part of that ongoing exchange between surface and depth. Even within the mantle's seeming uniformity, there are layers and boundaries, transitions where minerals reorganize into new forms. Around 400 kilometers deep, the olivine that dominates the upper mantle shifts into a denser arrangement known as wadsleyite, then into ringwoodite, each phase marking an adaptation to the increasing pressure. These changes alter how seismic waves move through the Earth, revealing to researchers the hidden stratigraphy of stone. And yet, despite all these transformations, the flow continues, steady, cyclical, unstoppable. It is motion slowed to the pace of continents, a form of stillness that only the Earth can know. Scientists have come to understand the mantle's behavior through indirect clues, the tremor of earthquakes, the paths of seismic waves, the chemistry of volcanic rocks. Every eruption brings to the surface a whisper of what lies below, carrying minerals that crystallized deep in the mantle and cooled on their long ascent. From these samples, geochemists reconstruct the story of the deep Earth, how it differentiates, how it circulates, and how it sustains the surface above. In some volcanic regions, such as Hawaii or Iceland, magmas rise from plumes that may begin near the core mantle boundary itself, ascending through thousands of kilometers like heat through a candle flame. These plumes bend the Moho upward, pressurizing the crust, and in time, burst forth as islands, tiny windows into the power below. If the Moho marks the threshold, then the mantle is the realm of slow transformation. It is where the Earth's heat is stored, where gravity and chemistry conspire to maintain equilibrium. The energy that escapes through the crust is but a fraction of what circulates within. Over eons, this energy drives the drift of continents, the endless rearrangement of the surface that has seen supercontinents like Pangaea form and fracture again. To imagine this movement is to imagine time itself flowing, the collision of plates that births mountains, the rifting that opens oceans, the quiet subsidence that swallows ancient seabeds. The mantle's convective rhythm also shapes the climate of the planet, though indirectly. When volcanic gases escape to the surface, they release carbon dioxide, sulfur, and water vapor into the atmosphere, elements once locked within the deep Earth. These emissions regulate temperature and, over millions of years, balance the carbon exchange between rock, ocean, and air. Without this connection, the Earth might have long ago frozen or boiled. The Moho, acting as a valve between mantle and crust, allows this deep dialogue to continue, ensuring that surface life remains possible. In this way, the mantle is both origin and regulator. Its steady convection maintains the magnetic field by feeding energy to the core, sustains tectonic movement, and moderates the slow cycles of carbon and water that nourish the biosphere. When the mantle stills, the planet will cool, the plates will halt, and the world as we know it will cease to renew itself. Yet such an ending is measured not in centuries, nor in millennia, but in the unfathomable scale of planetary time. Until then, the mantle moves, invisible but eternal. If one could journey downward through the crust, through the heat and darkness, and cross the Moho, one would not find a single, sharp change but a gradual metamorphosis. The rocks would become denser, richer in magnesium and iron, their colors deepening from gray to green to near black. The air would vanish, replaced by pressure so immense it would press the breath from the lungs before the thought of pain could form. Temperatures would climb past 1,000 degrees, then 2, then more, until light itself seemed to blur. And in that oppressive stillness, one might feel the slow pulse of the planet, not through sound or motion, but through an omnipresent, almost sentient vibration, as if the Earth were dreaming. Such a descent is impossible for us now, and perhaps it should remain so. Some boundaries are not meant to be crossed by force, but understood by listening. The Moho teaches patience, that knowledge of the deep comes not from intrusion, but from observation. We learn through echoes, through the tilt of continents, through the chemistry of stones that have traveled upward unbidden. And though we may never stand upon the mantle, we know that it sustains every step we take above it. When humanity first turned its gaze toward the earth beneath its feet, it was with a sense of curiosity that bordered on reverence. The ground was always there, solid and dependable, yet it concealed a mystery more profound than the stars overhead. For centuries, philosophers and naturalists speculated about what lay beneath the crust, whether it was hollow, fiery, or filled with unknown metals and vapors. But as geology matured into a science, the Moho emerged not as a mythic cavern or molten sea, but as something far subtler, a line of change, an invisible horizon separating two worlds. And soon, scientists began to wonder, could we reach it? Could we, with our tools and machines, pierce the crust and touch the mantle itself? The first serious attempt came in the mid-20th century, at the height of a new scientific optimism. It was a time when the boundaries of exploration seemed limitless, the same era that dreamed of lunar landings and nuclear-powered submarines also dreamt of drilling to the mantle. This ambition took form in a project known simply as Moho. Conceived by American scientists in the late 1950s, its goal was breathtaking in its simplicity and audacity: to bore a narrow shaft through the oceanic crust, which, being thinner than continental crust, offered the shortest path to the Moho. In 1961, off the coast of Guadalupe Island, the first experimental holes were drilled. A ship named Crust, retrofitted for deep-sea drilling, hovered in the Pacific swells, its position held steady not by anchors but by a then revolutionary system of dynamic positioning, a forerunner to the technology used by today's oil platforms. The crew lowered strings of pipe nearly 4 kilometers through the water, then continued down hundreds of meters into the basalt below. Each segment of pipe was added by hand, each rotation monitored with care, as the drill bit chewed its way into the seabed. They did not reach the Moho. The hole extended only about 183 meters into the crust before the project ran out of funding. But the implications were enormous. For the first time, humans had drilled into true oceanic rock, material born at mid-ocean ridges and cooled in the darkness of the abyss. The samples retrieved were priceless, fragments of basalt that told a story written in iron and silicon, recording the Earth's slow magnetic reversals and the chemistry of the deep. Though Project Moho ultimately collapsed under political and financial pressures, its spirit lived on. The technology it pioneered, deep ocean drilling, dynamic positioning, continuous core sampling, became the foundation of modern marine geology. Decades later, the deep-sea drilling project and its successors, including the Ocean Drilling Program and the Integrated Ocean Drilling Program, would take up the mantle of subsurface exploration, mapping the structure of the ocean crust and the sediments above it in exquisite detail. Each expedition extended the reach of human understanding a little further, tracing the gradients of temperature, pressure, and composition that lead toward the Moho. Other nations, too, sought the same boundary. In the Soviet Union, during the 1970s and 80s, an extraordinary effort unfolded on the desolate tundra of the Kola Peninsula. There, far from the sea, engineers began drilling straight down through continental rock, granite and gneiss that had formed billions of years before. Their goal was the same: to reach the Moho, though the continental crust here was far thicker, nearly 40 kilometers deep. The Kola Superdeep Borehole, as it came to be known, became the deepest artificial hole ever made by humankind. For 24 years, the drill advanced, inch by inch, often halting for months at a time as bits wore down or equipment failed under the crushing conditions. By 1989, the borehole had reached a depth of 12,262 meters, deeper than any mine, deeper than the deepest ocean trench. Yet it was still less than 1/3 of the way to the mantle. The rock temperatures at that depth exceeded 180 degrees Celsius, far hotter than expected, and the granite, once thought solid, behaved like plastic, closing in on the drill and seizing it. Eventually, progress stopped. Still, the Kola borehole yielded revelations. It uncovered microfossils in rocks over 2 billion years old, suggesting that ancient life had once existed at depths previously considered sterile. It revealed seismic discontinuities and water trapped in crystalline structures far below where any free fluid should exist. Most importantly, it confirmed that the Earth's interior was far more complex, and far more alive with geologic activity, than any model had predicted. To this day, no one has physically touched the Moho. The deepest drilling efforts, whether in oceanic crust or continental shield, have come within only a few kilometers of it, and the challenges grow exponentially with each meter gained. The heat alone would warp steel and melt lubricants, the pressure would collapse the narrow borehole like soft clay. Even if we could reach it, extracting a sample intact and unaltered by the journey would be an almost impossible feat. Yet in another sense, we already have reached it, through sound, through mathematics, through the subtle listening of seismic waves. Instruments buried in the earth and stationed across the oceans detect the echoes of earthquakes that pass through the Moho, bending and refracting as they encounter changes in density. From these signals, geophysicists construct maps of the boundary, tracing its contours beneath continents and seas alike. The Moho undulates, rising beneath ocean ridges, plunging deep below mountain ranges, and thinning where ancient crust has been stretched or fractured. Every time an earthquake ripples through the earth, it becomes a conversation between crust and mantle, a dialogue in pressure and vibration. Each tremor we record is another letter in the language of the deep. In recent decades, arrays of seismometers have revealed that the Moho is not a perfect, sharp line, but a zone of gradual transition, a boundary smeared by melting, infiltration, and deformation. In some places, basalt from the crust percolates downward into the mantle, crystallizing into new minerals. In others, peridotite from the mantle intrudes upward, cooling into gabbro or basalt. The Moho, it seems, is less a wall and more a conversation, an ever-shifting negotiation between two domains of rock. And so, while the dream of physically drilling to the Moho remains unfulfilled, our understanding of it has deepened in quieter ways, through patience, through listening, through inference. The effort to reach it by machine may have failed, but the effort to comprehend it through data and theory has succeeded beyond what those first dreamers of Project Moho could have imagined. Humanity has learned to study the inaccessible not by breaking it open, but by letting it speak in its own language of vibration, magnetism, and gravity. The frontier remains, silent and untouchable, but we no longer see it as an obstacle. We see it instead as a teacher, the reminder that not all exploration means intrusion, and not all boundaries must be crossed to be understood. Beneath the continents, the Moho lies deep, buried beneath layers of ancient rock that have been folded and refolded through billions of years of tectonic compression. Under mountain ranges, it sinks even deeper, 40, sometimes 50 kilometers below the surface, pressed downward by the enormous weight of the crust above. In contrast, beneath the open oceans, where the crust is thin and young, it rises sharply, sometimes within 5 or 6 kilometers of the seabed. The Moho, therefore, is not flat, nor fixed. It undulates like the surface of the sea, though its waves take millions of years to form. Its shape is a reflection of balance, the gravitational equilibrium between the rigid crust and the plastic mantle, a principle geophysicists call isostasy. Imagine a mountain range, its granite roots plunging deep into the earth, extending downward like an iceberg beneath the ocean. For every peak that rises above the surface, there is a corresponding mass of crust that sinks into the mantle, displacing it, pressing it aside, maintaining equilibrium. The Himalayas, for example, are not only the highest mountains on Earth but also the deepest in this hidden sense. Their roots extend far below the visible range, pressing the Moho down nearly twice as deep as beneath the surrounding plains. The same is true, in reverse, for ocean basins. Beneath the abyssal plains, the Moho rises close to the seafloor, drawn upward by the thinness of the basaltic crust above. The oceanic lithosphere is lighter and newer, and so the mantle comes close to touching the sea itself. These variations are the fingerprints of the planet's internal balance. When continents erode and their sediments wash into the sea, the weight distribution changes. Over time, the crust flexes and adjusts, the Moho moving silently up or down to restore equilibrium. This process unfolds over millions of years, imperceptible from the surface, yet it is the foundation of the planet's long-term stability. The Moho is the hinge on which the lithosphere rests, accommodating the slow tides of mass that pass between land and sea, mountain and trench, erosion and uplift. Seismic imaging has revealed that this equilibrium is more complex than once believed. In some regions, particularly at active continental margins where one plate dives beneath another, the Moho may split into multiple layers or become blurred by mixing. The descending slab of oceanic crust carries with it sediments, water, and other volatile materials that interact with the overlying mantle. This process generates partial melting, a thin layer of magma that can smear the boundary, creating zones of weakness and fluid motion. In these regions, the Moho becomes a transitional realm, neither purely crust nor purely mantle, but a mosaic of both, interlocked in a perpetual exchange of minerals and melt. Underneath ancient, stable regions of the continents, the cratons, the story is different. There, the Moho is clear, sharp, and still. These crustal roots, formed billions of years ago, have long since cooled and thickened, becoming rigid anchors of the lithosphere. The mantle beneath them is unusually cold and chemically depleted, its density reduced by the extraction of lighter elements during ancient melting events. This buoyancy is what allows the continents to float high on the mantle, resisting subduction, persisting through the slow rearrangements of tectonic time. To the deep earth, a craton is an island of quiet, a place where motion has nearly ceased, where the Moho lies undisturbed for eons. In contrast, beneath mid-ocean ridges, the Moho is alive with activity. Here, molten material continuously wells up from the mantle, spreading outward as the tectonic plates drift apart. The crust is born directly above the boundary, where melt crystallizes into gabbro and basalt. The Moho at these ridges is not static but constantly renewed, moving upward and outward as the seafloor grows. Beneath the ridge axis, it may even disappear entirely, replaced by a lens of magma that connects directly to the mantle. The moment the new crust solidifies, it begins its slow journey away from the ridge, cooling, thickening, and drawing the Moho downward as it contracts. By the time this crust reaches an ocean trench tens of millions of years later, the Moho beneath it has sunk deep and hardened into a rigid plate, ready to be consumed by subduction once more. The oceanic Moho, then, is part of a cycle, birth, aging, and death, repeated endlessly across the planet. Each ridge, each trench, each spreading plain is a different moment in that cycle. The mantle rises, melts, solidifies, sinks, and melts again. It is a slow heartbeat, millions of years per beat, but it sustains the entire surface world. The continents drift not as separate entities but as passengers upon this moving base, carried along by the slow conveyor belts of the mantle below. When seismologists listen to earthquakes passing beneath both ocean and land, they can hear these differences. The crust above the continental Moho rings with complex, scattered echoes, reflecting its fractured, heterogeneous nature. The oceanic Moho, by contrast, produces a clean, sharp reflection, a sign of its relative simplicity and homogeneity. Yet both boundaries share one essential feature: they mark the point at which the rocks begin to behave differently, to flow rather than fracture, to transmit the planet's deep heat rather than store it. These thermal gradients are what shape the life of the Moho. Heat from below softens it, allowing mantle material to intrude upward. Cooling from above strengthens it, causing partial melting to freeze into crystalline forms. Over long timescales, these processes act like breathing: expansion and contraction, intrusion and solidification, all maintaining the dynamic balance between crust and mantle. Even though the Moho lies far beyond human reach, its influence is everywhere, in the rise and fall of coastlines, the building of mountains, the drifting of continents, and the steady renewal of ocean floors. Every topographical feature we see, from the deep trenches to the lofty peaks, is mirrored by a counterform beneath the Moho. Where there is height, there is depth. Where there is weight, there is displacement. The Earth, in its quiet equilibrium, is always seeking balance. The Moho is the unseen line along which that balance is achieved, adjusted, and endlessly renewed. Where one tectonic plate slides beneath another, the world changes. The crust, once the solid floor of an ancient ocean, is drawn downward into the mantle, swallowed into a place where temperature and pressure rise beyond comprehension. This process, known as subduction, is one of the most powerful yet graceful motions on Earth. It is here, along these deep convergent margins, that the Moho bends and twists, caught in the act of being rewritten. The boundary does not stay still, it folds, fractures, and at times dissolves into magma. Beneath subduction zones, the Moho is no longer a quiet line. It becomes a place of transformation, a melting frontier between the dying crust and the living mantle. As an oceanic plate begins its descent, it carries with it sediments, seawater, and the chemistry of the surface world. These materials, though seemingly insignificant, play an extraordinary role once they are dragged into the depths. Under pressure, the water trapped within the oceanic crust and sediments begins to escape. This release occurs gradually, like a slow exhalation, as minerals dehydrate and their molecular structures collapse. The liberated water rises upward into the overlying mantle wedge, a zone of rock just above the subducting slab, and there it performs its silent magic. Water, in this hidden realm, is a catalyst of change. It lowers the melting point of the mantle rock, allowing partial melting to occur where otherwise the temperatures would not suffice. The mantle wedge becomes a crucible of molten material, generating magmas that slowly rise through the crust. Over millions of years, these magmas coalesce and erupt, forming chains of volcanoes that trace the outline of subduction zones, arcs that stretch across the planet like necklaces of fire. The Andes, the Cascades, the Japanese archipelago, the vast Indonesian arcs, all of them are born from this interaction between water, mantle, and subducting crust. At these margins, the Moho cannot be neatly defined. The downward moving slab drags part of the boundary with it, while rising melts from the mantle blur the distinction between crust and mantle above. The seismic signature of the Moho here becomes diffuse, as if the Earth's layers are whispering over one another rather than speaking in distinct voices. This dynamic zone, sometimes called the melt channel, extends for tens of kilometers, filled with magma lenses, fluid pathways, and zones of metasomatism, where the mantle is chemically altered by the influx of new elements from above. It is a place of deep alchemy, where the ingredients of future continents are mixed and stored. Every volcanic arc on the surface owes its existence to this concealed exchange. As the subducted crust melts and mixes with the mantle material, it produces magmas enriched in lighter elements, silicon, aluminum, potassium. These rise to form granitic and andesitic rocks, the foundational materials of continental crust. Over geological time, this process accumulates new land, recycling the oceanic crust into continental mass. It is a slow, continuous process, an invisible construction that has, piece by piece, built the continents themselves. Beneath the arcs, the Moho becomes an active boundary of creation, a zone where the old Earth is reborn in molten form. If one could see the interior of a subduction zone as though it were transparent, the image would be breathtaking. A descending plate sliding into the mantle at an angle, curling like a ribbon, above it, a wedge of partially molten mantle glowing faintly with residual heat, above that, a chain of volcanoes stretching across thousands of kilometers. Between them lies the Moho, warped and uneven, bending with the descending plate, sometimes breaking, sometimes merging into zones of melt. The crust and mantle here are not distinct, but partners in a dance of perpetual renewal. And yet, even in these violent-seeming places, everything moves slowly. The subducting plate creeps downward at a rate of only a few centimeters per year. The formation of a volcanic arc may take tens of millions of years. To human perception, this is motionless, unchanging. But on the scale of the planet, it is constant, unstoppable flow. The rocks bend, the fluids move, and the Moho adjusts itself continuously, a living boundary adapting to the needs of a restless planet. The seismic images captured beneath modern subduction zones have revealed astonishing detail. In some regions, researchers have detected double Mohos, two distinct seismic boundaries, one associated with the descending slab and another with the overriding crust. Between them lies a complex region of partially molten rock and metamorphosed sediments. It is a layered memory of the collision, frozen in seismic echoes. In other areas, particularly beneath old, stable arcs, the Moho has been obliterated entirely, replaced by broad transition zones where crust and mantle have mixed so thoroughly that the distinction is meaningless. This variability is not chaos but evolution. The Earth, through subduction, is constantly renewing itself. Oceanic crust, dense and saturated with water, is recycled into the mantle. In return, new crust is born at spreading centers, completing the endless cycle of creation and destruction. The Moho, in this context, is the thread that stitches the two halves of the process together, the boundary that passes from existence to dissolution and back again, depending on where in the cycle one looks. Beneath the trench, it sinks, beneath the ridge, it rises. Beneath the arc, it glows with the faint heat of Genesis. Even the continents owe their survival to this process. Without subduction, without the constant birth and death of the Moho, the crust would grow too thick and too cold to sustain convection. The planet would become inert, its surface frozen in time. Instead, the subduction cycle keeps the Earth alive, maintaining its magnetic field, renewing its mountains, refreshing its oceans. The Moho is not merely a line of separation, it is the junction through which the deep Earth communicates with the surface, transferring heat, matter, and even the chemistry that sustains life. If one listens carefully to the seismic murmurs beneath a subduction zone, one can hear that conversation. The tremors of earthquakes trace the descent of the slab, the slow, deep quakes mark where the crust bends and dehydrates, the faint, rhythmic pulses of tremor reflect fluids moving upward through the mantle wedge. These are the voices of the Moho, the planet speaking to itself in tones too deep for human hearing, yet as orderly and measured as breath. At the mid-ocean ridges, the planet opens itself like a slow-moving wound, and from that wound, molten rock rises. It rises not in sudden violence but in a long, unbroken breath, a constant exhalation of the deep earth. This is the birthplace of oceanic crust, the point where mantle material crosses a critical threshold and becomes something new. Here, the Moho is not a line of destruction, as it is beneath subduction zones, but a line of creation. It forms where ascending mantle melt cools and solidifies, separating the rigid basaltic crust from the ductile peridotite beneath. But just as in all things geological, even creation here is not simple. The Moho at the ridge is young, hot, shifting, and incomplete. It is being written even as it is being erased. Beneath the ridge axis, the mantle ascends because of decompression rather than temperature alone. As it rises, pressure decreases faster than heat dissipates, and the solid rock begins to melt fractionally. These partial melts collect into channels, merging into larger conduits that eventually feed magma chambers just below the surface. From these chambers, magma intrudes upward into cracks, cooling into a dense lattice of gabbro and basalt. When it finally reaches the seafloor, it erupts, quenching instantly upon contact with seawater to form pillow lavas, those bulbous, overlapping formations that make up the visible layer of new oceanic crust. The process seems almost mechanical, but it is one of the most fundamental acts of planetary renewal. Every second, along thousands of kilometers of mid-ocean ridges, new crust is born. The entire surface of the oceanic crust is replaced roughly every 200 million years, meaning the seafloor beneath our feet is always temporary, always migrating away from its fiery cradle. Beneath it all, the Moho defines the threshold between what was once molten and what still flows freely. It marks the point where the mantle's partial melt gives way to the newly solidified crust, though in truth, the transition is gradual, a zone of mixed material, porous and shifting. Seismologists who have studied these regions describe the ridge Moho as fuzzy, a word that feels oddly human for such an ancient boundary. The seismic waves that probe downward through the crust return not a single sharp reflection but a broad band of scattering. This tells us that the Moho here is not a crisp surface but a gradient, tens of kilometers thick in places, where melt lenses, frozen intrusions, and partially solidified rocks all coexist. Some scientists have proposed that the Moho beneath fast-spreading ridges, such as the East Pacific Rise, is continuously under construction, its shape fluctuating with the rhythm of magma supply. Others, studying slower-spreading ridges like the Mid-Atlantic Ridge, find the boundary more discontinuous, patchy, and chaotic, reflecting the irregular delivery of melt from the mantle. The energy moving through these systems is immense but almost invisible. The magma itself flows at a pace that could be outrun by a walking human, and yet, over time, it builds entire ocean basins. The cooling crust migrates outward, thickening as it moves away from the ridge. As it cools, it contracts, becoming denser and sinking deeper into the mantle. This slow descent changes the structure of the crust, and the Moho deepens with it. Near the ridge axis, it may lie just 4 or 5 kilometers below the surface. At the margins of ancient oceanic plates, it may rest more than 10 kilometers down. The Moho, therefore, is not static. It travels with the crust it helped create, moving outward, cooling, solidifying, and eventually descending again into the mantle at subduction zones. This eternal recycling is one of the most perfect examples of balance the planet maintains. Matter ascends and descends, melts and reforms, in an endless dialogue between heat and pressure. The mantle gives birth to crust, and the crust, in time, returns to the mantle. In this way, Earth keeps itself alive, like a heart that never stops beating. The Moho, in this analogy, is the pulse line, the faint boundary where energy passes between two forms of being. It is the moment between states, between fluid and solid, between life and decay. And yet, there are places where this process falters, where the mid-ocean ridges seem to pause, or where the crust fractures into deep faults that plunge toward the mantle. In these rift valleys, the Moho can come startlingly close to the surface. Seismic studies along the Atlantic and Indian ridges have revealed areas where mantle rocks, peridotites, are exposed directly on the seafloor, their olive-green crystals visible to remotely operated cameras. These exposures are rare windows into the boundary itself, as if the Earth has momentarily lifted its veil to show the raw material beneath. When such rocks are sampled, their chemical signatures tell stories of melting, mixing, and exhaustion, of how the mantle has been stripped of its fusible components through repeated melting episodes. The Moho in these regions is not so much a line as a scar, the trace of a process that has burned itself out. The interaction of magma, water, and rock at the ridge also fuels one of the most remarkable phenomena in the ocean, hydrothermal circulation. As seawater seeps down through fractures in the young crust, it meets the heat of the magma chambers below. The water heats rapidly, reacts with the surrounding rock, and becomes enriched with metals and minerals. When it finally escapes back to the seafloor, it erupts as black or white smokers, venting plumes of mineral-rich water into the ocean. These vents not only deposit massive sulfide mounds but also sustain entire ecosystems of organisms that live without sunlight, feeding on the chemical energy of the vent fluids. All of it, the chemistry, the biology, the very existence of these systems, depends on the precise structure of the crust and its underlying moho. The cracks that guide the water, the permeability that allows circulation, the distribution of heat, all are governed by the invisible architecture of the boundary below. Even after billions of years, the mid-ocean ridges remain a mystery. We have mapped them, drilled them, even sent autonomous vehicles to their depths, yet their internal structure remains partly hidden. The Moho, especially, resists definition. Some scientists argue it is a petrological boundary, the place where basalt turns into peridotite. Others say it is a seismic illusion, a change in velocity caused not by composition but by temperature and grain structure. Whatever it is, it serves as the deepest footprint of creation, the quiet mark left behind by a planet that has never stopped forming itself. If one could stand on the seafloor above a spreading ridge and listen, not with ears, but with instruments tuned to the slow pulse of the earth, one would hear the soft crackle of new crust forming, the faint hiss of water boiling in unseen chambers, the tremor of magma chambers adjusting to pressure. Beneath all of it, the Moho would hum like a deep, continuous note, the sound of rock becoming rock, of mantle and crust trading identities in a ceaseless exchange. It is a sound that has been playing for 4 billion years and will likely continue long after every continent has shifted, merged, or disappeared. Beneath the continents, the Moho takes on a different character altogether. It is no longer a youthful, molten line of birth but an aged, deeply buried threshold, cold, stable, and enduring. Here, the crust is not a thin film but a thick, layered mosaic built over billions of years. Some parts date back to the earliest solidification of the planet's surface, the relics of Earth's first experiments with stability. The Moho beneath these ancient continental interiors lies far deeper than that beneath the oceans, sometimes more than 70 kilometers down, hidden beneath the weight of granite, gneiss, and metamorphosed sediments that have been folded, crushed, and heated by the long patience of time. To the instruments of geophysicists, this continental Moho is a quiet, subdued reflection. Seismic waves slow as they travel through the low-density rocks of the crust, then suddenly accelerate upon reaching the denser mantle below. But unlike the oceanic Moho, which forms freshly and predictably, the continental version is more complex, layered with history. It does not always present as a clean division. Instead, it can be irregular, patchy, even duplicated, evidence of a planet that has stitched itself together many times through the long cycle of collision and rifting. When continents collide, as they did to form the Himalayas, the crust thickens, crumpling like fabric pressed together under unimaginable force. In such regions, the Moho can be buried to depths exceeding 70 kilometers, forced downward as the two continental plates push against each other. The pressure and heat at these depths transform ordinary rocks into new forms, shales become schists, granites recrystallize, and the once solid Moho itself becomes a broad transition zone of deformation. Seismic reflections blur, suggesting not a single boundary but a gradation of density and composition, where crustal materials are slowly being converted into mantle-like rocks through processes that take tens of millions of years. In contrast, beneath rift zones, those stretched regions where continents begin to split apart, the Moho rises toward the surface. As the crust thins and the mantle ascends, partial melting may occur, intruding basaltic magmas into the lower crust. Over geologic time, these intrusions can thicken and harden, welding the crust and mantle together in a kind of frozen dialogue. In both extremes, collision and separation, the Moho evolves. It breathes with the movement of the plates above it, deepening and rising, thickening and thinning, a boundary that is alive in its slow, deliberate way. The nature of the continental crust itself also influences the character of its Moho. In the old cratonic regions, those ancient cores of continents such as the Canadian Shield, the Baltic Shield, or the Pilbara Craton in Australia, the crust is both thick and cold. These stable blocks have survived for billions of years with little tectonic disturbance. Beneath them, the Moho is thought to be sharp and well-defined, a clean interface separating buoyant granitic crust from the dense, depleted mantle lithosphere below. The rocks here have long since cooled and locked into place. The seismic waves that pass through them return crisp, consistent signals, suggesting that the Moho has not changed for eons. It is a fossil boundary, a preserved trace of Earth's earliest structure, untouched since the Archean age when the planet was still learning to differentiate itself. But even within these stable regions, there are mysteries. Deep seismic surveys occasionally reveal hints of multiple reflectors, parallel lines that suggest more than one boundary. Some geologists interpret these as the remnants of ancient subduction zones, frozen within the crust when early protocontinents collided. Others see them as the scars of massive intrusions, where upwelling mantle once pawned beneath the crust and solidified, creating what are now invisible layers of density. In such interpretations, the Moho is not a single line but a composite, built through episodes of magmatic underplating and metamorphic transformation. In younger continental regions, such as the western United States or the East African Rift, the Moho appears more diffuse. The crust there is warmer, thinner, and more dynamic. Hot plumes from the mantle rise intermittently, weakening the base of the crust and blurring the transition between crust and mantle materials. In these regions, seismic velocities change gradually with depth rather than abruptly, implying that crustal and mantle rocks have mixed or that high temperatures have softened the distinction between them. It is in such zones that the boundary feels most ambiguous, as if the planet itself has momentarily forgotten where one layer ends and the next begins. One of the most fascinating aspects of the continental Moho lies in its ability to preserve memory. Every orogeny, every mountain-building event, leaves its imprint upon it. Beneath the Appalachian Mountains, for instance, the Moho bears the signature of multiple collisions, stretching back over 500 million years. Beneath the Himalayas, the boundary is warped and doubled, reflecting the ongoing convergence of India and Asia. In Siberia and Antarctica, it records the silent endurance of crust that has not moved significantly for over 2 billion years. Each variation tells a story of heat, pressure, and time, the slow choreography of a planet perpetually sculpting itself. Drilling into the continental Moho has long been a dream of geologists. The deep drilling projects of the late 20th century, such as the Kola super-deep borehole in Russia, sought to reach it. The borehole extended more than 12 kilometers into the earth, but even there, the Moho remained elusive. The rocks became hotter, denser, and more metamorphosed, but the seismic boundary, where the crust ends and the mantle begins, lay still deeper. What the drill revealed instead was the complexity of the crust itself, alternating layers of gneiss, amphibolite, and schist, each folded and recrystallized by the slow violence of tectonic history. The Moho, it seemed, was not a single barrier to be breached but an ever-receding threshold. Today, most of what we know about the continental Moho comes not from drilling but from listening. Seismologists record the way earthquake waves bend and reflect as they move through the planet. The faint echoes from the Moho, known as PMP or SMS phases, are isolated and analyzed, their delays and strengths mapped across regions to build images of the deep structure. These maps reveal variations in Moho depth that correspond to mountain belts, basins, and cratons, allowing scientists to see the hidden architecture beneath the continents. Still, even the most detailed of these images are blurred, because the Moho itself is not uniform. It is an ancient, uneven surface, like the underside of a continent that has been lifted, folded, and remade countless times. When one contemplates this buried boundary, hidden beneath tens of kilometers of rock, it is difficult not to sense a kind of reverence. It is the surface upon which the continents rest, the invisible foundation of all terrestrial life. Every mountain, every river, every city sits atop the crust, which in turn floats upon this mysterious threshold. The Moho supports the weight of everything familiar, yet it remains untouched, silent, and almost entirely inaccessible. Beneath the great mountain ranges of the world, the Moho bends and folds like a sheet of heavy fabric pressed between converging forces. It is here, under the vast compressive weight of colliding continents, that the boundary between crust and mantle becomes most distorted, most complex, and perhaps most revealing of the Earth's dynamic nature. The Himalayas, the Andes, the Alps, all of them conceal beneath their towering summits a hidden mirror image, a downward extension of the crust that dives deep into the mantle, forming what geologists sometimes call the root of the mountain. These roots, though invisible, are immense, often as deep as the mountains are high, counterbalancing their mass and maintaining the planet's equilibrium through the principle of isostasy. In these regions, the Moho can be buried to astonishing depths, sometimes more than 70 kilometers beneath the surface. But it is not simply pushed downward like a slab of rigid material, it is reshaped, thickened, and folded by the slow movement of the crust itself. The rocks above it, granites, schists, marbles, and gneisses, are subjected to pressures and temperatures so great that they begin to flow plastically. Over millions of years, the entire crust behaves less like a solid and more like a viscous medium, deforming under stress and transferring mass laterally. Within this process, the Moho becomes not a fixed line but a fluid interface, one that migrates, deepens, and sometimes even duplicates as the mountain continues to grow. In the Himalayas, seismic studies have revealed a complex structure beneath the surface, where the Indian plate plunges beneath the Eurasian plate. The crust here is extraordinarily thick, nearly twice the global average, and within it, scientists have detected multiple reflective layers. Some of these may represent fragments of the original Indian crust, subducted but not yet assimilated into the mantle. Others may be slices of mantle rock that have been dragged upward by the immense pressure of collision. The result is a transitional zone, perhaps several kilometers thick, where crustal and mantle materials are interwoven, a blurred Moho that refuses to settle into simplicity. The same complexity is seen in other mountain systems, though expressed differently depending on their tectonic history. Beneath the Andes, where the oceanic Nazca plate slides under the continental South American plate, the Moho undulates with the rhythm of subduction. In some places it dips steeply, tracing the path of the descending slab. In others it rises, arching upward beneath volcanic arcs where mantle melts intrude and thicken the crust. The Andes are not static mountains, they are constantly being built from below as magma ascends, solidifies, and adds new layers of material to the base of the crust. This magmatic underplating, as it is called, slowly raises the surface, expanding the mountains from within and altering the geometry of the Moho as it goes. What these examples reveal is that the Moho is not a mere geological relic but a living boundary, one that responds to every movement of the lithosphere. When plates converge, it deepens, when they pull apart, it shallows. It behaves almost like the skin of a vast, living organism, elastic in some regions, brittle in others, recording the stresses and strains of a planet forever reshaping itself. And within these hidden regions, at depths beyond human reach, the rocks themselves tell the story of transformation. Basalts metamorphose into eclogites, granites into garnet-bearing gneisses, and the dense, olivine-rich mantle material beneath begins to melt and mingle with the crustal residues above. The chemistry of these exchanges defines the mineral composition of the mountains and even the gases that emerge at the surface. One of the most remarkable aspects of these deep interactions is how slow and silent they are. The crust does not crack suddenly but creeps and flows, deforming at rates of only a few millimeters per year. Yet over tens of millions of years, such motion builds entire mountain chains and redefines continents. From a human perspective, this timescale is unfathomable, beyond any frame of experience. But from the Earth's perspective, it is simply the rhythm of its breathing, an endless cycle of uplift and erosion, creation and dissolution. The Moho, in this sense, is not the line that separates but the membrane through which the planet exhales its geological life. There are regions, however, where this balance is disrupted, where the crust becomes so thick and dense that it begins to sink under its own weight. Beneath the Tibetan Plateau, for example, some studies suggest that portions of the lower crust have detached and dripped into the mantle, forming convective plumes that rise elsewhere as renewed magmatic activity. This phenomenon, known as lithospheric delamination, is one of the most dramatic ways in which the Moho can be reconfigured. It demonstrates that the crust and mantle are in constant negotiation, exchanging material in ways that blur the very definition of what each layer is. Seismic imaging of such regions has revealed patterns reminiscent of fluid motion, eddies, folds, and tongues of high-velocity rock descending into lower-velocity regions. The Moho, instead of appearing as a flat, uniform reflector, becomes a chaotic landscape of peaks and troughs, a subsurface mountain range of its own. This revelation has forced geologists to reconsider their understanding of deep Earth dynamics. The boundary, once thought to be static, is now seen as active, mutable, and in some sense alive, a responsive participant in the planet's continual rebalancing of heat and density. Beneath volcanic arcs, where oceanic plates sink beneath continental ones, the story becomes even more intricate. As the descending slab of oceanic crust is pushed deeper into the mantle, it carries with it water trapped in hydrated minerals. When these minerals are heated, they release their water, which rises into the overlying mantle wedge. The introduction of water lowers the melting point of the mantle rocks, generating magma that ascends toward the crust. This magma, in turn, accumulates near the base of the crust, solidifying into dense, mafic layers. Over time, these intrusions can thicken the crust, pushing the Moho downward, or even fuse with it, creating hybrid zones where crust and mantle materials coexist. This process of subduction and magmatic growth links the Moho directly to volcanism at the surface. Every volcanic arc, whether the Andes, the Cascades, or the Japanese islands, is sustained by these deep interactions. The eruptions that light the sky are but the visible expression of chemical reactions taking place tens of kilometers below, at the interface between crust and mantle. There, in the slow mingling of elements, the Earth transforms its interior into the materials of the surface. It is an alchemy of immense patience, one that shapes continents, builds oceans, and sustains the cycle of renewal that defines the living planet. To stand at the foot of a mountain range is to see only the surface of this vast process. Beneath one's feet lies a labyrinth of structure, a world of hidden currents and silent heat. The Moho runs through that world like a great, unseen river, guiding the flow of energy and matter from the depths toward the light. Though we cannot touch it, it touches everything, mountains, oceans, and the steady trembling of the earth itself. In the deep trenches of the oceans, where one plate slips beneath another, the Moho begins its final transformation. It is here, in the subduction zones, that the boundary between crust and mantle ceases to be a boundary at all and instead becomes a process, one of descent, compression, and transfiguration. The oceanic crust, once born at a distant ridge and cooled by millions of years of exposure to the abyss, is drawn downward, returning to the interior of the earth from which it came. This slow and inevitable journey marks the closing act in the great tectonic cycle, and the Moho, once clear and firm, is dragged into a region where definitions blur and rock becomes liquid memory. At the surface, The evidence of subduction presents itself as a trench, an immense depression that marks the point where one plate dives beneath another. The Mariana Trench, the deepest of them all, reaches nearly 11 kilometers below the surface of the Pacific, deeper than any mountain rises above sea level. Yet even this immense chasm is only the visible trace of a descent that continues hundreds of kilometers beneath it. As the oceanic plate bends downward, the crust fractures, groans, and releases energy in deep, resonant earthquakes. Along the plane of the descending slab, these earthquakes can be mapped as a line, known as the Wadati-Benioff zone, that traces the path of the sinking crust as it plunges into the mantle. In this vast and silent movement, the Moho is stretched, tilted, and eventually consumed. What was once a horizontal boundary between crust and mantle becomes vertical, folded into the architecture of the subduction interface. The rocks that composed it, dense gabbros and peridotites, are compressed, metamorphosed, and ultimately transformed into entirely new materials. Under the extreme pressures of the upper mantle, basalts from the oceanic crust change into eclogites, their mineral grains rearranged into denser forms. The mantle peridotite, in turn, reacts with fluids released from the slab, producing zones of serpentinization where olivine transforms into serpentine minerals. These reactions alter the strength and buoyancy of the subducting plate, determining how and where it bends, breaks, or melts. As the plate descends deeper, it enters regions where temperatures and pressures rise beyond the capacity of solid rock to remain stable. Water and other volatiles, released from the hydrous minerals, rise into the overlying mantle wedge, lowering its melting point. This partial melting generates magma that ascends slowly, feeding the volcanic arcs that line the edges of subduction zones. From the Aleutians to the Andes, from Japan to the Philippines, these arcs are the surface expressions of a process that begins at the Moho's dissolution. Every eruption is the echo of this descent, the exhalation of a planet that constantly recycles itself through fire. But not all of the subducting crust melts. Much of it continues its downward path, entering the deeper mantle, where it becomes part of vast convective cycles that stir the Earth's interior. Some of this material may eventually re-emerge at distant ridges, reborn as new oceanic crust millions of years later. In this way, the Moho is both created and destroyed, over and over again, its fragments dispersed and reincorporated into the fabric of the mantle. It is not a permanent structure but an ever-renewing interface, a threshold that travels through time as much as through space. Seismologists who have studied subduction zones find that the Moho behaves strangely there. In some cases, it disappears entirely from seismic reflection profiles, as though the contrast between crust and mantle has been erased. In others, it appears doubled, suggesting that parts of the crust have peeled away or that portions of mantle material have been accreted onto the base of the overriding plate. Beneath the Japanese islands, for instance, seismic studies reveal two distinct reflectors separated by several kilometers of mixed rock, a chaotic melange where fluids, melts, and fragments of the descending slab intermingle. This chaotic zone is where the crust is effectively digested, its components chemically redefined as they merge with the deep earth. The temperature gradients in these regions are steep and complex. While the upper part of the subducting plate remains relatively cool due to its long exposure to the ocean, the deeper parts heat rapidly as they descend. This uneven heating creates zones of weakness where fluids accumulate, migrate, and trigger earthquakes. The interplay between these fluids, the brittle rocks above, and the ductile mantle below governs the behavior of subduction-related seismicity. Some earthquakes rupture catastrophically, releasing massive amounts of energy, while others creep silently, their motion too slow to be felt. In all of this, the Moho's remnants play a role. Its composition, structure, and metamorphic transformations define how energy moves through the descending crust. The fate of the Moho in these zones is one of dissolution and rebirth. As the subducting slab moves deeper, it enters the transition zone between the upper and lower mantle, roughly 400 to 700 kilometers below the surface. Here, minerals rearrange again, becoming denser forms. Spinel turns to perovskite and magnesiostite, and the physical properties of the rocks change dramatically. At these depths, the concept of a crust no longer applies. The Moho, as a separable boundary, ceases to exist. What remains are the chemical traces of its former self, slight variations in composition that persist in the mantle for millions of years, subtle whispers of an interface long since absorbed. It is a humbling thought that the same boundary which defines the very base of the continents, the same invisible plane that underlies every ocean floor, is destined in time to vanish. The Moho is not eternal. It is a transient structure, a surface of passing contrast in a planet that endlessly erases and redraws itself. The subduction zones remind us of this impermanence. What goes down will someday return, reshaped, reconstituted, and unrecognizable. The rocks that once formed a portion of oceanic crust may one day rise again as volcanic islands or granite mountains, their journey marked by the memory of having once crossed the Moho. And yet, for all this activity, the process remains astonishingly slow. From ridge to trench, the life cycle of an oceanic plate spans tens to hundreds of millions of years. The descent into the mantle occurs at only a few centimeters per year, a pace imperceptible to human senses. But across geological time, that slow motion builds worlds, recycles oceans, and sustains the balance of heat and mass within the Earth. The Moho's part in this cycle is both fundamental and ephemeral, an interface that defines the crust even as it guides its dissolution. If one could somehow follow a piece of rock from the Moho of an oceanic ridge down into a subduction trench, one would witness its transformation through every possible state, melting, recrystallizing, compressing, and, finally, merging into the convecting mantle. In that long, quiet journey, the boundary ceases to be a line on a map and becomes a living process, an expression of the Earth's own breathing. Far beneath the reach of subduction zones, below even the transition layer where minerals reshape under immense pressure, the Moho's remnants drift into the deep convecting mantle. Here, the temperature soars beyond 1,000 degrees Celsius, and the rocks, though solid by human standards, move with a viscous slowness that, over millions of years, behaves like fluid. In this vast interior, the boundary that once separated crust from mantle becomes nothing more than a chemical trace, a faint memory carried within a current of perpetual motion. These fragments, rich in basaltic and hydrated materials, sink and mingle with the paratitic host of the mantle, and though they vanish as distinct structures, their influence lingers, subtly changing the way heat and elements flow within the deep earth. Convection in the mantle is a process as slow as it is monumental. Heat generated by radioactive decay in the Earth's interior, along with the residual warmth from planetary formation, rises toward the surface, while cooler, denser material sinks back down. The result is a planetary heartbeat that turns over on the scale of hundreds of millions of years. Through this endless stirring, the ancient pieces of Moho that once framed long-lost ocean basins are carried downward, circulated through the mantle, and sometimes caught up in vast thermal upwellings that will one day return them toward the surface. In this grand cycle, the Moho is reborn not as a line, but as a movement, a pulse within the deep mantle that connects the planet's crustal history to its interior life. Seismologists studying the deep mantle detect curious features called ultra-low velocity zones, patches where seismic waves slow dramatically, hinting at regions of unusual composition or partial melt. Some of these zones, they suspect, are formed from subducted crustal material, once part of the Moho, that has accumulated at the base of the mantle, 2,900 kilometers down. Over geological time, these accumulations become the seeds of mantle plumes, great columns of hot, buoyant rock that rise through the mantle and eventually break through the crust as volcanic hotspots. The Hawaiian Islands, the Galapagos, and Iceland all stand as surface witnesses to this deep recycling. What once lay beneath the floor of an ancient sea, pressed against the Moho, can, after eons of silence, reappear as an island chain bathed in fire. Within this deep interior, time itself behaves differently. A single convective cycle, from the sinking of a slab to the emergence of a new one, may take hundreds of millions of years. Rock that begins its descent today could remain hidden for a span longer than the entire existence of complex life on Earth. It is a world of immense patience, where the physical and the temporal merge into one vast continuum. The Moho's memory drifts within this system like sediment in a slow-moving river, its presence marked not by visibility but by chemical anomalies, slightly enriched isotopes of strontium, neodymium, or lead that betray its crustal origin. These geochemical fingerprints allow scientists to trace the Moho's descendants, linking volcanic rocks at the surface to materials that once lay far beneath the crust. The deep mantle is not uniform. It is a landscape of extremes, domains of hotter, lighter material interwoven with cooler, denser regions that descend in long, sluggish curtains. The remnants of the Moho often settle in these cooler zones, dragged downward with subducted slabs and preserved from melting by their relative density. In seismic tomography, they appear as shadowy shapes, cold tongues sinking toward the core mantle boundary. But not all remain trapped. Some, heated by the surrounding mantle, eventually soften and rise again in narrow plumes. These plumes ascend through thousands of kilometers of rock, carrying with them the faint signatures of the crusts they once belonged to. When they reach the surface, they manifest as basaltic eruptions that form new oceanic islands or expand continental rifts. The cycle closes quietly, invisibly, the Moho reborn through fire. At the very base of the mantle, just above the liquid outer core, lies the D layer, a strange, thin region of partially molten rock and complex mineral structures. It is here that some scientists believe the ghosts of the Moho linger the longest. Compressed into dense, stable phases, fragments of ancient oceanic crust may accumulate and remain there for billions of years, forming chemical reservoirs that influence the evolution of the entire mantle. These reservoirs are thought to feed the great plumes that rise intermittently through the mantle, shaping surface geology on a planetary scale. The connection between the Moho and these deep structures suggests a continuity across unimaginable depths, a bridge between the most superficial and the most profound regions of Earth's interior. To imagine this is to envision the planet as a breathing organism, its outer skin constantly shed and renewed, its internal organs pulsing with heat and motion. The Moho is the connective tissue between these realms, the threshold through which material passes as it transforms from crust to mantle and back again. Its destruction and subduction zones is not an ending but a renewal, a momentary transition in a cycle without true beginning or conclusion. Every continental drift, every volcanic eruption, every earthquake that rumbles through the crust participates in this eternal process. The very continents we stand on are built from the recycled dust of ancient ocean floors that once rested against forgotten Mohos. And yet, even in this unbroken cycle, the Moho remains elusive. It is neither fixed nor uniform, it is a dynamic horizon, constantly shifting, dissolving, and reforming. The more precisely scientists attempt to define it, the more it seems to resist confinement, like the blurred edge of a mirage. Seismic instruments detect it, gravity surveys hint at it, and yet direct observation remains nearly impossible. No drill has ever pierced through the crust deeply enough to reach it. The deepest borehole ever attempted, the Kola super-deep borehole in Russia, descended over 12 kilometers but still fell short by several kilometers. Temperatures and pressures rose faster than expected, making further descent impossible. The boundary remained untouched, its mystery intact. In this sense, the Moho occupies not just a geological space but a psychological one. It represents the limit of human reach, the veil that separates the known from the unknowable. Scientists can describe its echoes, simulate its properties, and infer its movements, but the direct experience of crossing that boundary remains beyond us. It is the final unvisited frontier of our planet, a region that defines the edge of human exploration as much as it defines the structure of the Earth itself. To contemplate the Moho, then, is to confront a form of stillness that exists within motion, a boundary that is everywhere and nowhere. Beneath our feet, it lies waiting, folded beneath mountains, stretched beneath oceans, dragged into the mantle, reborn through volcanic fire. Its existence is as constant as the turning of the earth, yet its form is always changing. It is the quiet heartbeat of geology, pulsing unseen through the solid body of the world. There is something profoundly human about our desire to touch what lies beneath, to peel back the layers of the familiar world and glimpse the machinery that turns beneath its surface. The Moho stands as both a physical and symbolic boundary in that pursuit, a reminder that the planet we call home is not a static sphere of rock, but a living system of constant motion, renewal, and hidden depth. It is strange to think that after centuries of study, we still know more about the surfaces of other planets than we do about the floor beneath our own feet. The crust we walk upon is, in planetary terms, only a delicate rind, thin, fractured, and floating upon currents of molten stone. And yet, we have never crossed its deepest threshold. The Moho remains untouched, unreachable, a whispering line in seismic echoes that suggests where one world ends and another begins. Those who have studied it often describe a sense of awe at its simplicity. It is not a wall or a barrier, not a solid line that can be seen or touched, but rather a change in the very nature of matter itself. Above it, the rocks are brittle, capable of breaking and fracturing, their composition familiar: granites, basalts, sediments, the foundations of continents and oceans. Below it, the rocks transform. The minerals reorganize, dense olivine and pyroxene replacing the lighter feldspars of the crust. Here, light elements like silica give way to heavier, darker materials. The transformation is silent, gradual, but absolute. It is the place where Earth's identity shifts, where the record of surface processes gives way to the deep time memory of the planet's formation. In this way, the Moho can be seen as the planet's subconscious, a region where the dreams of creation are still being shaped. Every mountain that rises, every ocean that deepens, every continent that drifts owes its birth to the energy moving through that hidden plane. It is not the deep mantle that drives the crust's motions directly, but the subtle interaction at the boundary where solid meets fluid, where cold plates meet the slow, hot current beneath them. The Moho, invisible and intangible, is the translator between those realms. Through it, heat flows upward, pressure dissipates, and matter crosses from one form to another. It is the whisper between two worlds, the brittle silence of the crust above and the rolling thunder of the mantle below. It is humbling to consider that the Moho we study today is not the same Moho that existed when life began, or even when the continents first gathered into the supercontinent Pangaea. The crust has been renewed countless times, recycled through subduction, melted, and reborn. Each iteration carries a trace of the last, chemical ghosts of ancient oceans locked into the minerals that rise again as new land. The Moho has shifted with each cycle, rising and falling like a tide over geological epochs. Its current shape is the latest expression of billions of years of quiet transformation, a single frame in a film that has been playing since the Earth first cooled from molten fire. Beneath the Pacific, the Moho lies shallow, sometimes only 5 or 6 kilometers below the seafloor. Beneath the continents, it plunges deep, 30, 40, even 70 kilometers down, where the roots of mountain ranges anchor themselves into the mantle. These variations, though vast in scale, occur gradually. There is no cliff, no sudden edge, only a long, slow transition that can take thousands of meters. The difference between crust and mantle is measured not in appearance but in vibration, density, and mineral structure. Seismic waves are our only eyes in this darkness. They travel through the earth like ripples in an endless pond, their reflections and refractions sketching the faint outline of the Moho's undulating form. It is through these delicate patterns of motion that scientists have mapped the unseen, revealing the contours of a world that will never be reached by hand. Even so, the dream of reaching it persists. Decades ago, a project known as Project Moho attempted to drill through the oceanic crust to the mantle beneath. Engineers believed that by starting in the deep ocean, where the crust was thinnest, they might finally touch the boundary itself. The effort began off the coast of Mexico, where the seafloor lies miles below the waves. Ships equipped with early dynamic positioning systems lowered drilling pipes into the abyss, and for a time, progress seemed possible. But the technology of the 1960s was not yet equal to the challenge. Costs spiraled, political will waned, and the project was abandoned before it could reach even a fraction of the required depth. The hole they left behind, now filled with sediment and seawater, remains as a quiet monument to human curiosity, a reminder of how close we came, and how far we still are. The attempt did not end there. In later decades, new programs, such as the Integrated Ocean Drilling Program, sought to continue the mission. Advanced drilling ships like the Chikyu, a marvel of Japanese engineering, were built to extend our reach. The Chikyu has drilled deeper into the oceanic crust than any vessel before it, retrieving cores of solid basalt that reveal the processes of the deep earth in unprecedented detail. Yet, even this modern wonder has not reached the Moho. Each kilometer gained brings exponential increases in temperature and pressure. Rock turns plastic, tools deform, and equipment fails. The earth resists intrusion not out of malice, but through the sheer force of its natural state. The Moho remains where it has always been, silent, patient, unbroken. There is a certain poetry in that resistance. For all our advancements, there remain boundaries that define the limit of human knowing. The Moho teaches us humility. It reminds us that even with satellites orbiting distant planets and probes exploring the outer reaches of the solar system, there are mysteries beneath our very feet that remain as unreachable as the stars. The deep earth holds its secrets close, speaking only in tremors, in the slow migration of continents, in the rise and fall of mountains. Its language is time itself, and we are only beginning to understand its syntax. Perhaps it is fitting that the Moho remains unseen. Its value lies not in its visibility, but in what it represents, a living threshold, a reminder that Earth is not a finished world but an evolving one. It is a symbol of continuity, of change without chaos, of stillness within movement. To imagine it is to imagine the world breathing slowly, endlessly, through stone. It invites reflection on our own position within that rhythm, small, temporary beings tracing the edges of an immense and ancient pulse. And so, as we listen to the faint echoes that return from deep within the planet, we hear more than seismic data. We hear the slow whisper of time, the echo of every earthquake and eruption that has ever shaped the world. Beneath all the noise of civilization, beneath the clatter of cities and the crash of waves, that pulse continues, steady, unwavering, eternal. The Moho, unseen yet ever present, is the quiet divider that unites the two halves of our world, the fragile crust of our awareness, and the deep, unknowable heart that sustains it.